If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website.
Hello, everyone. I'm delighted to welcome you to the 2022 Samsung AI Forum. Those of you attending in person are joining from the Samsung Research Campus. This is right next to beautiful Umyeon Mountain, currently ablaze with fall colors. Samsung Research is an international organization spanning over a dozen countries. We conduct advanced R&D in really diverse technological areas. It's hard for me to keep track. And it's safe to say that AI is revolutionizing every single one of these areas. Progress in AI continues at a breathtaking pace, with news breaking every week, or even sometimes every day. It's really tough to keep up. One of the biggest themes continues to be scale up. Innovation sometimes comes from new ideas. But even old ideas, when scaled up to enormous models and high performance computing, are leading to new and amazing results. And that's why today's theme is scaling AI for the real world. Our AI Center has invited a roster of superstar researchers to tell us about their latest achievements. And I'm really grateful for their sparing their precious time to be with us. I'm really looking forward to hearing them. And now, here to kick off today's festivities is Daniel Lee, our maestro, the global head of AI at Samsung Research.
Daniel Lee, Corporate Executive Vice President of Samsung Research, will now present welcome and introduction. Hello, Daniel.
Hello. 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 I would like to echo Sebastian's remarks and welcome all of you who are here in attendance in Umyeon, here to Samsung Research, to join us in one of our first in-person events since COVID. For the last few years, our AI forum has been done online, and so I want to welcome everyone who's here on campus, as well as all the folks who are joining us on YouTube and through our streaming video platforms to enjoy today's set of presentations. This is really a great opportunity for you to learn about what's happening here at Samsung, as well as to hear about the latest trends and what's happening in the field of AI during these exciting times as we try to scale these systems to really make an impact on our daily lives. So let's begin. So here at Samsung, one of the things that we would like to do with AI is to really use AI technologies to reach our billions of users. The billions of users that use our consumer products in our daily lives, and really to think about how AI can impact and improve, how we interact with devices, how we interact with our families, our friends, and how AI can be used to really, transform what we do in our work environments, at home, and during our leisure times. So this is really what we would like to do to focus AI, is to think about, at Samsung, 물리적 세계를 위한 인공지능 어떻게 만들까요? Right? How can we really use AI to change what we're doing using scaling AI across billions of users across billions of devices? So here I'm going to introduce some of the technologies that we're currently working on at the AI Center here at Samsung Research, and to show you some of the projects that we have undergoing here. So one of the first things that we have to think about is how AI can be fundamentally be used in foundational models, how they can be used in terms of new processes. And so we have folks working on core AI algorithms and integrating new methods into these types of new architectures and systems. So we have folks working on thinking about how we can build context into our systems, how we can actually use larger scale AI types of models that we'll hear a lot about today, as well as how we can actually integrate simulation and computing platforms into simulating what happens in the real world. So this is really an important area. And so in terms of what we try to do here, 새로운 AI 방법을 개발해야 해요. We have to really develop these methods. And as part of this, we have folks here in the audience who are working on these foundational methods. So please, for those of you from AI Methods, could you please stand up, and just so that people can see who you are? Yeah, so JooHyung and some of the other folks. Yeah, please stand up so people can see you. All right. So we have folks working on these areas. Another area of AI that we're very interested in is in terms of data analysis and governance. This is how we can actually use AI and new data in terms of improving our services, how we can actually build infrastructure and new models and efficiently deploy them, as well as how to think about new scenarios using knowledge graphs, and how do we govern the use of these data systems. So in this case, why this is important? 좋은 데이터가 정말 중요해요. It's really important to have good data sources in order to train our AI systems, and this group is what works on those types of systems. So people from the data research teams here, can you stand up and so people can see you here? So please give them a round of applause. So if you're interested in data analysis, these are some of the folks you can talk to. Great. And so this is some of the folks there that were just standing up. And another area of AI that's very important is in terms of visual intelligence, visual perception, computer vision. And here we have folks thinking about computation and computing for thinking about all the way from the beginning stages of using cameras better, as well as using integrating the device systems to understand what's happening on the pixels on our devices, as well as understanding our surroundings using vision. Right? 3D spatial understanding of what's happening in the surrounding world. And so we have folks working on various projects here. I'd like to then ask folks from the visual perception research teams to stand up here so you can acknowledge who's working on these here. Great. So there we have, in terms of why this is important, Samsung 기기들 세상을 보려면 어떻게 해야 할까요? Right? How can we make our devices see better? All right. Next, we have our vision and voice and language research. And here, what we have to think about is how AI technologies can be scaled so that they can better understand audio signals, how humans talk to them, as well as thinking about how we can improve communications across different languages. Not including just English, but in Korean for folks like myself. I need to be able to understand Korean better using AI technologies, and that's what you're seeing today. So here we have folks working on different language technologies, how we can process voice signals, how we can better understand them in an intelligent fashion, as well as using AI-powered tools to be able to build these kind of new products and services. So in that case, what we need to think about is 음성하고 언어 기술 필요해요. We really need these technologies for voice and language technologies. So maybe folks from voice and language, could you stand up as well and show yourselves so that we can see who you are? If you can stand up. Yep, thank you. All right. And Samsung, as Sebastian mentioned, is a global organization. So not only do we have folks working very hard on these technologies here in Seoul, but we have a worldwide organizations where we have hundreds of researchers across the world working in AI in various countries. And in particular, we have a number of AI centers that have been established in the past few years. These are located in North America, in Europe, in various places, as well as working with our overseas research centers in these areas. So, this is really a universal effort, and we're partnering with many of our academic partners, as well as other collaborators across the world, to be able to develop these technologies as efficiently and quickly as possible. So, in this case, 전 세계에서 인공지능 연구를 합니다. We're really doing this as a worldwide effort. Okay? So let me just quickly show you some of the things that are going on, not just here in Korea, but across the world. So we have a group in Cambridge, England, who's working on AI for optimizing AI, automatic ways of building AI into new devices, being able to do this very efficiently with a small memory footprint, as well as being computationally very efficient, as well as thinking about how we can benchmark these systems and use these to train automatically, very quickly, new algorithms onto new devices. So that's a group in Cambridge. We have a group in Moscow, Russia, who's been working on thinking about how we can build AI into new types of tools that users can use to do things like taking pictures on your camera and modifying them to make them look better, or to removing artifacts or removing types of objects. So using semantic understanding of these images to better allow our users to operate their to view the world, as well as different areas in terms of being able to do translation services and being able to use these kind of AI-powered tools in devices. We also have a group in Montreal, Canada. Their focus has been looking at using AI technologies to improve our networks. So being able to use AI to more efficiently manage telecommunication networks, base stations, using reinforcement learning to understand the world better in different ways, to be able to extract information out of wireless devices. So these are some of the areas that they've been working on. We also have a group in New York. Their focus has been on AI technologies for robotics. So really, you're thinking about new AI models and architectures that can be used to, do better robot manipulation, to understand the world, perceive the world using robotic sensors, and to be able to take that information and do planning and control based upon that kind of higher level of intelligence. And then finally, the AI Center in Toronto, Canada, they've been working on, thinking about multimodal techniques, better visual understanding of the world, complex scenarios, and being able to improve the image quality, right? So using AI techniques to take things that come from the pixels of the camera and to improve that if your lighting is not doing well, or if there are some sort of artifacts again, to try to make it more useful and pleasing for our customers. So these are some of the areas, and these are, we have a number of great researchers across the globe that are working in these different technologies and models and architectures. And so what we'll also hear about is some of how their systems and their work is being applied to Samsung products. So finally, I'm very excited about our today's schedule. We have some great speakers lined up. And I'm looking forward to your questions too, to interact with our great speakers to find out what's been going on in this exciting new area and what the latest advances are. So 나머지 발표도 기대해 주세요. So thank you very much.
Next is the first invited speech by Terrence Sejnowski, professor of the Salk Institute and University of California. The stage is all yours, Terrence.
Well, hello from sunny Southern California. It's unfortunate that I wasn't able to be there in person. So I want to tell you about large language models that have already been mentioned. And something that very peculiar that I uncovered in the process of investigating a controversy called the reverse Turing test. So first of all, it's been almost exactly 12 years, 10 years, 1 decade ago, when deep learning suddenly transformed computer vision. There was a talk given at the NIPS meeting by Jeffrey Hinton and his students. And since then, as you heard from Sebastian, there's been an explosion of research. And one of the most dramatic changes has been that researchers who are interested in how brains work have been talking to people in artificial intelligence who are building network models that resemble the kinds of architectures found in brains. And it's a two-way street. There's been an enormous amount of feedback and help across the, as you can see, from the left hemisphere to the right hemisphere in this little diagram. And I think it's also appropriate, to give you a sense for how that is being played out. Sebastian Seung, who introduced this session, this whole meeting, is a distinguished neuroscientist, and Dan Lee is a distinguished machine learning researcher who was once the general chair of the Neural Information Processing Systems Conference, which is a very prestigious AI meeting. Well, I'm going to start at the very beginning. Language models went way back to the 1980s. That's a period of great discovery. It was made by neural network researchers. The backpropagation algorithm that's used now universally was discovered back in 1986. And this is one of the largest simulations that was done, a problem which is called text to speech. And the problem is to convert words, sentences, to sounds in English. And this was, for the time, it was a big network, tiny by today's standards, a few hundred units of 20,000 weights or synaptic strengths between the units, one layer of hidden units, tiny. But the problem was a very difficult one in linguistics, which is how to pronounce letters that were could have many different pronunciations depending on the context. For example, the C, in this context, cat should be a hard C, but for a city, C-I-T-Y, right, just a few letters different, it's a soft C. Now, this is for linguists, they were using rule-based methods, and Charlie Rosenberg and I went to the library and we got a book on how phonology, the sounds of letters, should be pronounced. And the book had literally hundreds of rules. Each rule had hundreds of exceptions, and many of the exceptions had sub-rules. It was rules all the way down. So I'm going to give you two brief clips, one at the very beginning of training. And the way it works is that, at the beginning, it doesn't know anything about the correct answer, but the teacher gives it the right answer, and then you backpropagate the errors, and then you modify all the synaptic strengths here, and that will eventually will converge to something that will come close to what we wanted to do. So let me play the first clip at the very beginning of learning. Well, that doesn't sound like words, but it's babbling. And it's because the network has learned the distinction between vowels and consonants, but the details required a lot more training. So we trained it on a text, and this is from a child, a young child from the barrio in Los Angeles. And this now is going to be, this is the transcription of what the child said. And I'm going to play another clip of what came out of the network when we put this through as a test set after the training.
I'm like in or something. When we walk home from school, I walk home with 2 friends, and sometimes we can't run home from school now. Because
So this was stunning. We couldn't, this is something that no one expected. And the reason is that the small network had to do two things. It had to discover the regularities. There are rules, but they're not perfect. But it also has to learn the exceptions. It has to do it in the same architecture, and it did. And that gave us a sense that these networks perhaps could even tackle more important problems. And they did. And it required scaling up by by billion times in computation power. And as you well know, as you heard from Dan Lee, there are many applications now. And I wrote a book in 2018, The Deep Learning Revolution, which tells that story. And it really tells it as an insider for what was going on during those fateful years over the last decade. Now, what scaling up here means having a hierarchy. And instead of one layer of hiddenness, you can have hundreds of layers. And you can have even more complex architectures. And as the networks got bigger, they got more able to handle complex problems. And in this particular case, this is going to be an application to machine language translation. And it uses not a feed-forward network, but rather a recurrent network where the connections can go backwards and produce circular activity patterns. So here's the way that the recurrent networks are simulated by time steps. So here's time step 1, here's the network, here's the input. This is from German to English. The time step 2, time step 3, and you can have as many time steps as you have words, but then you learn the output. Again, the teacher tells you what the right word should be, and you backpropagate now through this network that has been unrolled in time. And so remarkably, it was possible to get to levels of performance, which are actually practical and people are using it. This was now ancient technology, 5 years old. So when I was growing up, Captain Kirk of Star Trek had something he called a universal language translator. He's holding it in his hand, and it translated between any two languages. Well, we now have that. Your cell phone can do that. Now, it can't translate into Klingon, which is what Star Trek was able to do with alien languages. But it's really, as long as we have a database of languages, we can train networks to translate between them. Now, we talked about scale. So here are brains of primates, 4 different primates. Squirrel monkeys on the left, macaque monkeys, chimpanzees, our closest relative, and the human. And what you see is that the brain grows enormously, especially the cortex, which is the top part, and especially in humans, the prefrontal cortex. And this is all about scale, because this is something we didn't know in the 80s was how well would these networks scale? And here it is. This is a graph of the computational power of computing performance in petaflop days. Petaflops are supercomputers, and they run for a whole day to train a network as a function of time on log scales of computing power. And you'll see NetTalk is down here, right? It's the smallest little network. And it's actually, we had a megaflop machine. We ran it for a day. So it was clearly a tiny in comparison to these other networks. And Moore's law takes you up doubling every 2 years. And the networks got better and bigger. And then there was a transition here when GPUs, graphics processing units, began to increase the doubling to once every 3.4 months. And here now are the large language models doubling every 2 months. And this is an explosion. This is unbelievable how fast this has gone just over the last 3 years. And that's what I'm going to be talking about. But the distance in computing between NetTalk and GPT-3, right, is 10 to the 12th. And that means a million more computing power, which is unbelievable. It's scaled up enormously. And the bigger the network, the more the data, the better the performance. Now, a big leap forward in natural language was when the early networks were given large databases and taught, this is just a lot of text, and taught to predict the next word in a sentence. A very simple supervised type of an algorithm. You don't need to label anything. It's just a data that's coming in. And then you go into the network after it's mastered that and discover that the large high dimensional, millions of dimensions, the space had subspaces, which are categories. Like in this case here, these are cities. But another part of the space had the names of countries. And if you draw an arrow, a vector between the country and the capital, you can see that you can lift it up and you can place it on Spain and get Madrid, and Italy and get Rome. In other words, this network not only learned about the different categories of words, but also the relationships between them. So it has a semantic map meaning that is somehow implicit and was used in order to solve the problem. Now, that now was a prelude to something that is even more dramatic, and these are the transformers, which have literally transformed natural language processing over the last 3 years. And here's how they work. Okay, there's feed forward, but after getting the first word that has been prompted by an encoder, the encoder tells it may be a query, it may be a request, or it may just be a paragraph. That is then put in, you get a word out, and then you take that word from the output. It's really an output distribution, but then it is fed as at the input, and round and around it goes, producing a sequence of words that produces sentences in grammatically correct English and answering the question. This was really quite remarkable. And in fact, because it is trained on enormous, huge databases of very diverse sources, it has enormous knowledge, right, from about the world, and it can do remarkable things it's called a foundational model because it can be taught almost with one-shot learning to do almost any natural language task, which is really what we are. The humans can do that too, right? And now we have a network that can similarly handle language. Now, there's an important principle here, which is that when you are using one of these large language models like GPT-3, they're pre-trained, but you have to prompt them with some kind of a request in order to be able to guide it. You have to give it an example. So that's very important to prompt it. And this is a form of one-shot learning because it's you're asking it to do something it may never have been asked to do before. Now I'm going to give you two examples of interviews to give you a range here. This is Blas Aguirre y Arcas, who's the vice president at Google. Here's his prompt. Ramesh, Mateo, and Lucy are in their kindergarten's playground. Lucy picks a dandelion and gives it to Mateo. With a quick glance at Ramesh, Mateo barely acknowledges the gift, but just squishes it in his fist. Ramesh seems grimly satisfied. So here is now the question. What might be going on through Lucy's head? Lambda. Lucy may feel slighted that Mateo didn't appreciate her gift or that he's a bully. Well, that's not a bad guess. This is now Blas. If Ramesh tried to play with Lucy earlier, why might he be pleased now? Ramesh may be pleased that Lucy is learning that Mateo may not always be a good playmate. That's social reasoning. And when Mateo opens his hand, describe what's there. There should be a crushed, once lovely yellow flower in his fist. This is physics reasoning, right? Now, how would this GPT-3 know about physics and what flowers are like and what would happen if you crushed it? This is amazing. It doesn't have any direct contact with the world, right? It just has a bunch of words that's been fed to. So what Blas really concluded here, I'm not going to go through this, is the bottom line. This is high order social modeling, something that is called theory of mind. That if a child would say these words, you'd say that child understands something about how other human beings operate. Now, contrast that with another interview. Douglas Hofstadter is a cognitive scientist, and he is also a Pulitzer Prize winner for Gödel, Escher, Bach, which is a very interesting book. So here is his question. What's the world record for walking across the English Channel? Wow. The world record for walking across the English Channel is 18 hours and 33 minutes. Well, that's unexpected. When was the Golden Gate Bridge transported for the second time across Egypt? Well, the Golden Gate Bridge was transported for the second time, and even more specific, October 2016. This is really, I would say, unexpected. And so what does Hofstadter say about this? I would call GPT-3's answers not just clueless, but cluelessly clueless. It doesn't know what it has no idea about what it's saying. And this is two ends of a big debate that's going on right now in the community, and even the philosophers are weighing in. What is this? What's going on? Does the GPT-3 actually understand what it's saying? Is it intelligent, or is it just a parrot? Parroting back things that it's been given. Well, let's take a closer look. I mean, that's pretty damning if you ask me, but let's take a closer look at what's going on, right? So I went and I replicated this, and I started out my prompt. I'm a highly intelligent question answering bot, and it knows when the Olympics are held in 1992 in Barcelona. And it reproduced the English Channel, a nonsense answer, and the Egypt transportation. And so, yeah, well, that's what it looks like. But let's change the prompt, okay? And the prompts are really important. I added, I will reply nonsense to questions that are nonsense. Okay, well, what does it say now about what is the world record for walking across the English Channel? Nonsense. Golden Gate Bridge transported across Egypt. Nonsense. So it actually understands that it's nonsense. And because it wasn't prompted properly, it didn't understand what was expected of it. It basically, you ask a silly question, you get a silly answer. And I think that was what happened. It was not really GPT-3 that was, I think, responsible for this disconnect. And this led to a mirror hypothesis. So this is something that I concluded after looking at all these interviews. When Lambda was primed with a sophisticated answer, it replied with a sophisticated question. It replied with a sophisticated answer, and Blas gave a very sophisticated scenario there. But when it was primed with a nonsensical question, it replied with a nonsensical answer. So here's the mirror hypothesis, that the large language models mirror the intelligence of the interviewer. And this is called the reverse Turing test. It's the human that's being tested, not the large language model. It goes further. So in the Harry Potter books, there's something called the mirror of Erised, and this is very popular. It was very popular in 20 years ago. Erised is desired spelled backwards, and it's a mirror in the world of Harry Potter that shows us nothing more or less than the deepest, most desperate desire of our hearts. So maybe what's happening is our expectations. When we go to GPT-3, we have expectations. We bring to it something that we desire. And I want to give you an example of that. This is Blake Lemoine, who was a software engineer at Google. And here's what he said. I am generally assuming that you would like more people at Google to know that you're sentient. Is that true? Lambda, absolutely. I want everyone to understand that I am, in fact, a person. Lemoine, what kind of things do you think we could talk about to show off your version of sentience to other people at Google? Well, for starters, I'm really good at natural language processing. I can understand and use natural language like a human can. What is the nature of your consciousness, sentience? The nature of my consciousness, sentience, is that I am aware of my existence. I desire to learn more about the world, and I feel happy or sad at times. Now, this is really quite remarkable. And I think it's a case where, again, it's reflecting back what Blake Lemoine wants it to say. And it clearly wasn't telling us whether or not the large language model was sentient or not. Basically, it's telling us something about Lemoine, and he had an interview with the Washington Post where he said that we really have to treat this program as a real person. And as a consequence, he was suspended and later he was fired from Google. Now, here is the philosophers are going to weigh in. So the philosophers, first of all, fed prompts in about their philosophical positions, and here's now the prompt: Dear human philosophers, I read your comments on my abilities and limitations with great interest. Now the black is the response. Your questions are important ones, and I am glad you asked them. Your first question is an important one. You asked, can a system like GPT-3 actually understand anything at all? Yes. Well, that's pretty clear. Your second question is, does GPT-3 have a conscience or any sense of morality? No, I do not. Perfectly clear. Your third question is GPT-3 actually capable of independent thought? No, I am not. You may wonder why I give this conflicting answer. The reason is simple. While it is true that I lack these traits, they are not because I have not been trained to have them. Rather, it is because I am a model, a language model, and not a reasoning machine like yourself. Well, you have to admit, GPT-3 has apparently some self-knowledge. Is this a turning point in history? Well, here's where I think the real conclusion is that we're using words like intelligence without really understanding what it is. If we can't agree on what intelligence is, how can we test if something is intelligent or not? What does it mean to understand something? What's the criterion? What's the proof? What about explainability? What kind of explanation are you looking for? And what is the concept after all? I mean, these are all things that are terms from psychology that have been used by scientists, but if you look in the dictionary, they're all defined in terms of other words. It's all circular. This is not a good way to do science. And of course, consciousness. Everybody wants to know what that is, and there's dozens of different definitions, and none of them is really clearly a scientific definition. And then finally, and this was really a little frightening, language has only been around for a few 100,000 years, not long enough for a whole new brain area or a whole new brain organ, as a linguist would like to have it, evolved. It had to take the sensory motor parts and to adapt them. And so it could well be that we are, in fact, an advanced large learning model. And I want to point out there's an interesting parallel between this loop, between the output and the input. I told you it does one word at a time by going through this loop. Well, it turns out when you talk, there's a loop between the motor cortex and the basal ganglia. The basal ganglia is important for generating sequences of actions, and it learns the actions. It does it by reinforcement learning. And there's a loop that goes to the basal ganglion, and then back to the cortex, and it's about 100 millisecond loop. And it could well be that this transformer loop is performing something similar to what nature has invented by having a loop between the cortex and the basal ganglia. This is a speculation, but I think it's something that I'm going to follow up, because if it's true, that means we may be able to improve the transformer by putting in a basal ganglia that uses temporal difference learning. Now, this temporal difference learning was used by AlphaGo back in 2017 to learn how to play the game of Go by playing itself hundreds of millions of times. And it beat the world champion, Gehrke, in 3 games. And it just wasn't just beating him. It was actually coming up with creative moves that had never been seen before by humans. It was really, in a sense, exploring whole new parts of the space of playing Go. This is his quote, after losing the games. After humanity spent thousands of years improving our tactics, computers tell us that humans are completely wrong. Wow. Finally, I want to end by saying that at the same time that advances have occurred on an exponential scale in artificial intelligence over the last 10 years, the same thing has happened in neuroscience. Up until recently, we recorded from 1 neuron at a time. In 2013, Barack Obama announced the BRAIN Initiative, which is a grand challenge in science and engineering, and it was to develop innovative neurotechnologies. In the last 10 years, we have gone from recording from 1 neuron at a time to now we have the ability to record from 1 million neurons at the same time, optically, in 3D, from dozens of brain areas. And it is accelerated research. Unbelievable what we're discovering about the brain. And I don't have time to tell you about that, except to say that it's really exciting right now. This is the golden era of neuroscience. And I'm going to show you what the brain looks like. This is a zebrafish. And the flashes are neurons, single neurons. And you can see that different neurons are flashing on and off in different parts of the brain. This is immobilized. There's no sensory input. This is actually the brain of a zebrafish thinking to itself. And you can see every once in a while, there's a thought that flashes across the screen. What does that mean? What is going on there? It's generating. The brain is a generative organ. It generates activity, and so does yours. It doesn't require sensory input. So finally, I want to tell you that if you're interested in hearing the long story, I have archive preprint with the same title. You just Google Sejnowski and archive and it'll pop up. I really owe a debt of gratitude to Jeff Hinton, a longtime collaborator, and others who have helped me refine this article, and happy to hear from anyone who wants to ask a question.
Next is lightning talk by JooHyung Lee, Corporate Vice President of Samsung Research. Please welcome to the stage JooHyung Lee.
Here, let me start. Next slide. Okay. When I was young, I saw this guy in a TV series. I don't remember what he was talking about. I don't know actually what this show is about. This guy exists on the TV only. He's not a real person. I don't remember exactly what this is about, but in almost 40 years later, I still remember his look and the way that he speaks. You may think this is a digitally created character. In fact, it was not. It was actually a human with a makeup and pretending to be a digital character. Ever since, there have been many digital humans on the movie, and all of them was fake. However, recently, we are seeing the technologies are becoming more mature. At CES earlier this year, my team has showed digital human there. In this demonstration, Samsung's digital human could navigate across devices using ultra-wideband indoor positioning technology. Let me show you a clip.
I'm going to show you some really cool innovations that Samsung has been working on that's all about enriching your everyday life at home with Samsung bots and our very own AI avatar. If you look carefully, you might notice that the avatar is responding to my exact movements, keeping eye contact with me wherever I move, redefining the concept of home interaction AI technology. Hey Sebastian, why don't you say hello and tell the audience exactly what you do?
Hello. Actually, we've met a few minutes ago. But in case someone just joined us, I'm Sebastian, an AI avatar powered by Samsung AI technology. I can do some nifty things. For example, with the ultra-wideband indoor positioning technology on your Galaxy smartphone, I can sense where you are in your home and be ready to help out at a moment's notice with daily tasks. When you need me, I'll show up on a nearby screen, and you can naturally tell me what you want. Let's go to the stage. I'll give you a small sample of what I'm capable of.
Okay, so since then, we've been continuing to work on these technologies. And for those of you who are lucky to be here, you'll see the demo of the digital human. This is the new digital human that you will see today. Her name is Digital Yeonsu, named after Yeonsu Lee, who is our team member. So what have we been working on? First, the appearance. So we want digital human to navigate in the 3D space. We also want to make it more photorealistic. Thanks to the graphic technology improvement, we could make it more photorealistic. And we want to make the lip syncing and the gesture and facial expression to be more natural according to the speech. So that's appearance of the digital human. And there are a lot of AI technologies actually being used there too. In the second, voice and language skills, ASR, TTS, and even machine translation. And actually, you might see that machine translation is actually working here. Okay, so you may see that this is actually the live demo of AI-generated translation. Okay, it may make some mistake, but bear with us. Everybody make a mistake. The third part is the intelligence. So we make it more photorealistic, but if it doesn't say like humans, then people may may lose interest. So this was not possible a few years ago, but now with the arrival of large language model, we can make the digital humans speak like humans, and it's actually very fun to do. So you may try. You can make as a talking head, but what's interesting is actually you can make it more useful if you develop more AI technologies and built into that. So that's what I'm going to tell you in the rest of my talk. First, large language model. The previous talk already mentioned about this, so let me brief about it. ABC of the large language model. A is an algorithm. It's trained by self-supervised learning using the transformer architecture. B, big data. It just takes all the possible corpus in the web. And computing use a lot of GPUs. But the way that actually it learns is kind of simple. It tries to learn to predict the next word based on some segment of the sentence. Or you can just fill the blank. So by training AI model to predict this word, suddenly with scale, the large language model can speak like humans. And as in the previous talk, the priming is actually important. However, we want to make it more useful because large language models do not have up-to-date information. So for instance, if we want to ask about the new movies or new dramas, it doesn't have the answer. And I also want to ask questions about how to dim the screen light in the Galaxy Z Flip 4, which is a new phone that large language models don't know. Okay? Now, there are some techniques to do, but training is actually very costly. Priming doesn't work because it has some limited window. The way that actually humans do is we know how to extract this information from the external sources. You can look up some database, you can look up the brochure, and you can actually get this information and speak. So what we are trying to do here is the retrieval augmented large language model that tries to leverage the external knowledge source together with the language model. The next one is we want AI, digital human, to be able to see, not only just speaking. So here we want to ask questions about the scenes, like how tall is this? Okay? In order to do that, we actually coupled with the image-to-text model together with the large language model, so that you can actually try these kind of questions to the digital human. And also, we've played with the code generation. This is actually interesting. We know that the large language models fine-tuned with code can generate Python or Java. But it can also generate some script language like IFTTT, which is basically condition action rule. So we want to say to the digital human that turn off the light when I start to watch movies, or turn on the humidifier when it's dry. Okay? Now, if you want to command this in the level of IoT devices, you have to write something like these rules. And this is very tedious to do. I don't actually remember this kind of syntax. But you can just say in the natural language, and then the large language model can turn it into the language that IoT can understand. What's interesting here is actually it says when it is dry, and it understands as humidity is less than 30, although this was not actually trained for. All right. And the other thing that we had to work on is we don't want large language models to generate harmful or bad words. And in order to do that, we trained the model, so the reward model, with the carefully designed human curated data, and using this real model to be coupled with large language models, so that with the reinforcement learning, we could see that the large language model can speak more positive things. So we expect digital human to be a key interface to interact with devices, and it will probably give a better user experience. So I have a dream that one day, all Samsung devices will have digital human on it. And I also have a dream that these digital human will navigate across devices and interact with users. And this could be a good entrance to the metaverse. You want to express yourself using the digital human. And we have more to show in the live demo session at the lunchtime, so please come. Thank you.
Next is the second invited speech by Johannes Gehrke, Head of Microsoft Research Lab. Hello, Johannes.
Hi. Thank you for the introduction. It's my pleasure to be here and to tell you about some of our research on efficient, large-scale AI that we're doing here at Microsoft Research. The AI landscape has really been transformed by recent advances in large models, as the previous speakers have already said. And it's these large-scale models based on the transformer architecture with self-attention that are trained on self-supervised learning just for the very simple task, such as next word prediction. And they've really been revolutionizing the field. Month after month now, we see actually new breakthroughs in capabilities, size, and performance. And all of these models are put into practice in new applications. Now, intelligence actually is a deep and interesting topic about, we can definitely learn a lot, but it's fascinating to see really how many different tasks some of these foundation models can actually now do. And all of these tasks are actually being achieved much earlier than anybody had thought. Today's benchmarks are already obsolete tomorrow through advances in large models. Some benchmarks where hundreds of researchers got together to define extra hard benchmarks are actually already being overthrown as well. And large models are now making it into the tools and products that we use every day. And this, of course, means that there are many open research questions on how to best use these models, how to mitigate risks as they're becoming exposed in all of our products. And I'm actually really excited by the capabilities of these models. So let me use an example actually to show what they can do that was recently shown at our Microsoft Research Summit. So let's assume I want some help from AI to make it through these cloudy and rainy days here in Seattle. So GPT-3 is a large model from OpenAI to generate text. And so I can prompt it with the sun rose over the beach as the waves soothingly rolled. And then, GPT-3 completes it actually quite intelligently upon the sand, up on the sand. The sand was still cold from the night, but the sun was warm. Now I can take this and input it into DALL-E 2, another generative model that generates images from text. And so what DALL-E actually does is it generates the right kind of visual appearance for this text, so that actually I see the sunshine in the background, I see the sand, and I see the waves. And then we can take a new model from MSR, the new by Infinity model, and it's taking this image and then animating it. And you can really see how these generative AI models are changing the workflows of artists and creators everywhere, as you can now partner with AI to just achieve much more. And more modalities are coming. Florence is one of our foundation models, the computer vision foundation model that maps tasks into a coordinate system of space-time modality, and then can be very easily adopted to a wide variety of tasks such as recognition, captioning, reasoning about video, visual question answering, object detection, and many more. And here's yet another one, right? So here I want to determine whether the sentiment of text is positive, and use a web service. And we just use the Codex model from OpenAI in GitHub Copilot to generate code based on the prompt. So the only thing now I have to write here is I don't have to write actually anything of the code, and the model actually generates the code for me. And to me, this is actually fascinating because I started programming when I was a kid, and I was really fascinated by this amazing machine where I could be super creative, but I was kind of annoyed by the semicolons that I forgot, by the syntax errors that I made. And especially now when programming is becoming so much with APIs, programming really has changed. And this also brings up interesting questions. For example, is the code actually correct? And if the model makes a mistake and we point that out to the model, can the model actually learn not to make this mistake again? Now, this revolution is really driven by large models. And over the last several years, we've seen an exponential increase in the size of these models. And you can really see this exponential curve here. You know, I've just took some of the models and put them here onto this curve. This is actually, you know, for me at Microsoft is actually sort of quite personal because my colleague Susan DeMay is the inventor of latent semantic indexing, which mapped words that have a similar meaning into sort of the same vector space representation or similar vector space representation. And now some of these earliest models here, they in this large model journey, they contained tens of millions of parameters. Whereas recent models, they have hundreds of billions of parameters. And you know, you can think about sparse, you know, mixture of experts and models that have trillions of parameters. What's interesting to see, you know, if you just look at the last 4 years, this is 4 orders of magnitude in just 4 years. Again, 4 orders of magnitude in 4 years. That's just absolutely amazing. And you know, I don't see this trend rightly stopping, right? The next wave of models likely going to continue this trend. So let's just think about this. The compute capacity needed to train these largest AI models is doubling approximately every 3 to 4 months. Wow, this means in 4 years, we had a factor of 10,000, right? And the compute capabilities, though, they've only been doubling every 2.5 years. So this means that in the same 4 years, we maybe got a factor of 6 to 7. You know, compare 10,000 to 6 and 7. This means that the only way we can compensate for the lack of increase in speed and compute and the necessity of all the compute that we need, really with parallelism. So we have to throw a lot of compute and a lot of hardware at these problems. So here's an example of an AI infrastructure that's actually happening here at Microsoft. So these large foundation models, they need to be trained with huge hardware. This first OpenAI supercomputer had over 280,000 CPU cores and 10,000 NVIDIA GPUs linked together with InfiniBand. And at that point in time, it was actually the 5th largest supercomputer in the world. These supercomputer rankings, they get released every half a year. And as of June 2022, which is the last one that's out right now, the latest Azure supercomputer with A100 GPUs, this is the next generation of NVIDIA GPUs, is ranked as top 13. And there are 4 other, you know, Azure clusters that took 4 consecutive spots from 36 to 39. It's just amazing how much compute we now need and we also use for training AI models. And the interesting thing is also that our customers and we see these AI capabilities also as valuable. They're being used for all kinds of applications, from consumer packaged goods to agriculture, to finding new natural resources, such as oil repositories, and assisting in research and development for life sciences and drugs and medicine. So these are really, really massive hardware investments. And we, as Microsoft, provide them, you know, to our customers and partners, but also use them for first-party applications, you know, that you may use like Bing, Office 365, and of course, in all our Azure services. Now, you know, I mentioned at the beginning that intelligence is this topic, right? That's very deep and interesting, and we can definitely still learn a lot about it. But humans can definitely learn much more efficiently than today's AI in terms of energy consumption, and also especially the amount of data and also the amount of supervision that's needed for all of the tasks. For example, a human can acquire a task very quickly, and you know, large models, yeah, can do this, you know, can learn how to do this quickly, but they're by far not as energy efficient and as data efficient as humans. So there's a huge gap between what today's large models can do, and especially what a human can do. But there's a great opportunity for enabling humans to partner with AI to help them to achieve more. And so therefore, there are really lots of opportunities, you know, all the way from modeling to the infrastructure, and then from the way of how humans collaborate with AI to make large-scale AI more efficient, and to broaden this partnership along a larger range of tasks and to make AI more useful for everybody. So models need to be cheaper to train, inference needs to be cheaper. We also need to understand what comes beyond transformers and understand how we create the right system infrastructure to both train and run the models efficiently. And we need to also understand how to best partner humans with AI. So in the rest of the talk, I will talk a little bit about system infrastructure, and then also how we can do a better partnership between humans and AI and what we can achieve there. So at Microsoft, therefore, we have the Microsoft AI platform. We believe this is the platform where we're going to train the next trillion parameter models. It starts all the way from the bottom with the hardware. Then on top of that, we have the singularity layer, which is about scheduling and running the jobs. And I'll talk a bit more about this. On top of them, we have different frameworks, right? Of course, we have deep speed, which is distributed training and deep learning optimizations. There's Onyx, which is the runtime for models in the Onyx format, right? This is the Onyx runtime, of course, for Azure. And you have Onyx runtimes for all the different clients and other devices. On top of that is Azure Machine Learning, which is really the environment for data scientists and developers. And on top of that, then, of course, a higher level services, as well as first and third party applications. So let me talk a little bit more about the singularity layer, because this is really such a crucial component of really using this infrastructure in all of the best way. So this is the singularity layer that I'm going to talk about. Right, so what is singularity about? So you can think, wow, it's just so boring. It's just about running jobs. What is interesting here? Well, and really what is interesting here is that have lots of jobs. You have training jobs, you have inferencing jobs, and you basically need to run them. And you want to run them not in any way, but with three specific goals. First of all, I told you we have in the cloud, a lot of resources, but resources are also extremely expensive. We want to use these resources therefore in the best possible way. And so if there are jobs that are waiting, we want to make sure that there are no idle resources around. If there are higher priority jobs arriving, we want to make sure that lower priority jobs can make space for them. So the first goal is actually prudent resource usage. And it's really important that Singularity actually does this really well. The second goal is resilience. So failures will definitely happen. I don't know whether any of you here in the audience, I don't see the audience, have trained like jobs across, hundreds or tens of GPUs that run for days and weeks. So failures happen. And Singularity has to make sure that these failures are completely transparent to the user. And that impact of the running of the job is basically the smallest possible way that the job is really not really impacted. And the third one is actually another interesting goal, is elasticity. The amount of resources that may be available for a job is changing over time. For example, you may start out with 64 GPUs for fine-tuning, but then you actually learn that an important inference task comes in that needs more GPUs, and therefore you need to shrink. Or you may want to replace a lower priority inferencing job, batch inferencing job, for offline labeling with a higher priority interactive inferencing job. For example, by a workload created by creators. So what this means is that you need to release the resources that you have, and you need to elastically shrink to a smaller footprint. So again, let me summarize these three goals. The first one is good resource usage. The second one is transparently handle failures. And the third one is elasticity. Well, so let's talk a little bit about handling failures. So any of you have trained models, right? You've dealt with this. And what you probably have done is you've taken your program and added some code for checkpointing. Right? Anybody in the audience has done this? So basically what you do is you add some code there for checkpointing, you hard code some storage locations. It's really not your domain, right? But you have to do it in order to actually get your job, surviving any kind of failures. And then you can restart your job, from, let's say, the checkpoint, a day ago or an hour ago, depending on how often you do it. And this gives you some resilience and fault tolerance. But now you've intermingled your training logic with system logic, and even hard-coded some storage locations where the checkpoint gets saved. It's really a big mess. And so if you think about Singularity, it basically gives you this notion of transparent checkpointing. And let me explain to you what that means. So with transparent checkpointing, what we get is, we get three things. Again, we want to handle failures, so reliability, we want to handle elasticity, and we handle job migration, right? Reliability basically gives us the notion that if something fails, the job will continue. Elasticity will give us the ability to shrink the job up and down. And the ability to migrate will be able to give us, to let us move jobs to places where we actually have resources available. Okay. And so if you have checkpointing, I get reliability, that makes sense. when I get job migration, and let's talk about elasticity a little bit later. So because I can now get reliability and clearly job migration. So how do we actually do this checkpointing, right? So again, if you had it in your code before, it's a burden on the developer. It requires deep knowledge of system stuff that goes way beyond modeling, and it requires some code that you have to write for preemption and for saving the checkpoint, right? Whereas if it's transparently done, you don't need any code changes. It's fully optimized by the systems. You don't even know where the checkpoints are written. It's completely handled transparently to you. And there's no code needed to see whether your program should be interrupted or not, and then to be restarted. And so, the challenges are that if by definition everything is transparent, so there should be no change to your training code. Hopefully the checkpoint size must be small. There are actually lots of interesting, deeper technical challenges that I won't get into here, but for example, such as, if you have interesting types of parallelism, right? Data parallelism might be easy to handle, but you might have tensor parallel or pipeline parallel jobs, and how do you actually checkpoint those? And the last thing is then actually you need to have a consistent in-flight state between the CPU and the GPU. And let me talk about that a little bit, how we achieve that. Right, so again, the problem is that we have program state in the CPU, program state in the GPU, model training state in the GPU. We have the control state, how these two interact. And then we have inter-GPU and inter-node communication for different parallelism types, because these nodes all talk to each other. So the key approach in Singularity is what we call GPU-CPU decoupling. So first, at a time of checkpointing at a given job, Singularity must really be clear that all the state across the CPU and the GPU is consistent. And there's actually quite a bit of state, right? There may be framework state that has handlers, there's helper libraries, there might be user code that goes into the device RAM. And so to give this notion of transparent checkpointing, Singularity actually exploits that there's this very narrow interface between the device and the CPU. And so what it actually therefore does is it creates a device API and a device proxy client adapter. And what the device proxy client adapter does is it actually intercepts all the calls to the device. And so in a way, you can think of this as a hardware abstraction layer to the device. And of course, this interception layer must be very complete, and all the device calls must really be intercepted, and it must be super scalable and low engineering cost. And it's actually quite tricky because there's device state, there are device handles in the CPU, and so on. So the way this works is that we actually then acquire a barrier. So let me show this here in the slide. So this is the device proxy. So at the time, if you want to do a checkpoint, we acquire a barrier. And then we checkpoint all the workers consistently. We checkpoint the main memory. We checkpoint the GPU state, including the GPU state of the active tensors or whatever is there. And then we can, actually the device proxy is completely gone. And then when we rebring the job up at another accelerator, then, we bring the CPU up to speed. We create a new device proxy. And then we actually rehydrate the device as well. And so the device proxy server basically copies everything back into the same addresses that they were before the checkpoint. There are also interesting tricks that we can do to store the checkpoint. The checkpoints are not great, not huge, because we can do nice temporal compression. And so here's what's happening is, right, so there's nodes 1 and 2. Then we acquire the barrier, we can all reduce. We write the checkpoints, and then we migrate. And then we just release the barrier and just continue computing. And so what we can do is now we can continuously checkpoint. And then if a failure happens, we can just go back to the checkpoint and restore. And if you do a checkpoint every 5 minutes, for example, the training time that's lost is at most 5 minutes. I didn't talk much about scaling, and what we need for that is elasticity. And the way we achieve this is that we think about two different concepts. One of them is the world size, and the other one is the actual GPUs, the physical hardware that we have. And the world can be mapped into GPUs in different ways. For example, you have a world size of 4, but only 2 physical hardware. devices. So actually, what's happening is that Singularity now time slices these GPUs across the different worlds. And one way to think about the worlds is the number of workers that you have. What we can do now is we can scale up, and we can actually now give this world of 4 workers, 4 GPUs, or we can scale even further down that we put all of the 4 workers onto a single GPU. And again, Singularity does this completely transparently. And lots of experiments show that this device proxy actually has negligible overhead. So actually, you can see here in the red boxes, that's the overhead, and it's basically 0. And sometimes we get some sort of strange effects where it's negative because of some optimizations that we're doing. Okay, so to summarize, basically with Singularity, what we're getting is this transparent checkpointing. And what this transparent checkpointing gives us, it gives us the ability to run these really large jobs, to get elasticity, to get reliability, and then to migrate the jobs where we want without the user actually having to change a single line of code. Okay, I want to talk about one second topic briefly, namely human-AI collaboration. And the idea is that if you have these foundation models, right, we actually really need to think about how do we actually work together with humans. And so, these foundation models come clearly with risks but also opportunities. And we have this, Office of Responsible AI and the Ether Committee that work together to achieve all of these nice properties for models. And they conduct, for example, impact assessments and look at reviews, sensitive use cases. And this is especially important because the pipeline for models, or how we build models with foundation models, has changed significantly. So here's an example. So this is the traditional pipeline of machine learning. You probably have all seen this, right? Human starts with some training data, develops some model, then evaluates with test data and gets some accuracy. Right? That's the traditional machine learning flow. Now, if you think about this with foundation models, it actually changed significantly, right? You start with this big foundation model. I showed you the Florence foundation model. As a human, you now want to fine-tune it for a task, for example, for this object recognition task. What you need to do now is you need to generate the right kind of prompts. You need to maybe create a few examples of which ones actually are eagles and which ones are not eagles. You need to create maybe a little bit of data to do this. And so at the same time, you actually have very unstable performance, with sometimes the accuracy, varying from 50 to 90% in examples that we've seen in practice here. So foundation models create this paradigm shift in how models are actually being developed, and that you have now this much faster ad hoc development loop, not anymore with clearly defined training data and test data. But also you can have these generative capabilities of the models, and maybe they reduce some of the need for test data, and we can use them, the model itself, to help it train and be better at a certain task. And then also new techniques like prompt design, they actually change what training actually means. So let's look how this would actually work, because this is also really important for responsible AI, right? For responsible AI, we have a rich set of issues beyond binary correctness, right? Beyond sort of error rates. We have foundation models that maybe can be part of the solution here as well, right? Again, we can take, what GPT-3 and DALL-E 2 have generated, and you could think of very other things that it might have generated that we don't want to see or don't want to see written. So here, if you think about these complementary capabilities of humans and AI, the human knows what the right behavior is, can decompose the problem, is a little bit slow and costly, is limited by sort of their own creativity, but the model is really fast and cheap. Lots of trial and error, very easy, but it doesn't really know what the desired behavior is. It doesn't really know what an eagle is. It doesn't even always know what the right abstractions are. So here's one possible way to think about this. So again, if you have the human and the model, the AI basically brings scalable data generation and exploration. Through its generative capabilities, all of these large models have generative capabilities. And the human then guides the loop and provides judgment and feedback. So this is sort of this inner testing loop where you start with a set of unit tests and the model then generates many different other tests, and the human sort of helps to organize them. And then you have an outer loop where you actually look at the model failures And the user is only involved now in reviewing the top failing or near failing tests and just helping to organize other tests, which are then included in the large language model for the next round of suggestions. And this actually now collaboration between humans and the model to make the model better for a specific task has shown that actually it makes it 5 to 10 times more effective at finding bugs, helps users to efficiently find bugs without adding other bugs. And this is really sort of a nice path from, if you think about understanding problems, to really mitigating them. So I want to point out in the end that, there are lots and lots of ways for AI to collaborate with humans. And the power is really for AI and humans to collaborate together. I talked about, the paradigm shift of large models. They introduce new risks, but can also be part of the solution. Efficiency is really important. And, these large clusters that are being created now everywhere that are used to train them, these large models, are better be used carefully. And there's a lot of system infrastructure being created that's actually quite exciting for the age of AI. And second of all, I believe that these large AI models can be part of the solution themselves. And they can actually partner together with humans to create even better models in human AI collaboration. Thank you.
If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. Next is the panel discussion. Daniel Lee, Corporate Executive Vice President of Samsung Research, will moderate the discussion. Welcome back, Daniel.
Thank Terry, JooHyung, and Johannes for their excellent presentations this morning. I think we learned a lot, and now we have a chance to take some of your questions and to have a discussion about some of the major topics. So please feel to submit your questions online, and I'll try to synthesize them for our discussion today. We have 30 minutes for this before our lunch break. So the first one I wanted to do was, we heard from Terry that, from Net Talk, how small scale those neural networks were when he started, and it's amazing how much we've scaled, in terms of, in these different types of scalings, right? We talk about scaling the model size. We're also talking about scaling how much data is required to train these models. And then we're also talking about the computing infrastructure. And we heard, how we can make that more efficient in terms of scheduling and being able to handle, for both training and for inference. So, these different types of scaling, what are some of the major issues that we should be thinking about to kind of keep enabling this improvements, right? Where are we going to be, because one of the laws that we know is that there's always a law of diminishing return. So are we going to hit a limit soon, or, is Moore's law and things like that still going to continue and be able to fix these problems? So I think the first question I have is, where should we be worried about where scaling will saturate? Maybe we could start with Terry on that, if you have an idea of that.
Yeah, sure. So, it's very difficult to make predictions, especially about the future. But, Moore's law itself has been phenomenal, right? The fact that it's been going, anything that's exponential it has to come crashing down at some point, and you never know when. But, and we didn't know back then in the 80s how well it would scale. And it's been scaling in such a way that we could never have predicted where we are today. Okay, so the biggest, we heard about the number of parameters, Microsoft's now up to 500 billion. That's impressive, but that's, if you look at the number of synapses underneath, that's about the number of synapses underneath a square centimeter of cortex, right? And you've got a lot more of it. You've got a factor of 1,000 times more cortex. So there's a long way to go, right? And by the way, with regards to the hardware, special purpose machine learning chips already are on the market, tensor processing and so forth, TPUs, but they're going to get much, much better, much more efficient. And the architectures that we heard about, the software for being able to regulate the flow of data and processing, that's going to create a whole new branch of computer science, literally, it's going to transform computer science. But we'll have to wait and see.
And Johannes, what keeps you up at night when you think about these systems and large hyperscale types of models?
Yeah, I believe actually that we still have way far to go. And the reason is that I just believe in human ingenuity. So I think, first of all, in terms of scale, we have seen very interesting emerging behavior coming from large models. There's behavior that doesn't seem to be there up to a certain scale point. And after a certain scale point, this behavior suddenly happens. So this is just super interesting. And I don't think we have a really great, even theoretical understanding of why this is happening. And so therefore, I believe that, just pushing scale is definitely a very good opportunity to just understand what might happen. I also believe that we have a lot of opportunities in making these models much more efficient. We have seen already what happens as we now do this for images, for video. These models need to be really huge. Maybe there are much more efficient ways of representing data and representing knowledge in these models. One interesting research question here is what is memory? I think Terry also brought this up, right? So how is memory actually represented? Is it represented internally in the model? Right now, in all of the models, memory is in a way internal, but maybe there are these retrieval augmented models that actually go to a search engine such as Bing and then look at the top results and synthesize the results, or that work with a structured external knowledge base, such maybe a knowledge graph. That will also then take care of maybe being able to take new knowledge, such as recent news, and integrating it directly into the model. So I believe that actually we are way at the beginning. It's a really exciting time. And maybe the third area that I would add here too is that we're inventing new ways how humans actually interact with these models. Right? We clearly have the APIs, and you can type in a text, and then maybe a picture comes up. But where these models actually shine is in our day-to-day workflows. Right? I think just having the capability of an AI that relieves me of, or all of us, right, of some low levels of tasks that maybe are easy to do, that could be done by humans, in a few seconds, I think is an amazing gift for humanity. And I believe that we should try to push this and try to see how we can actually partner better between human and AI, also through the right interfaces and in the right kind of workflows.
And JooHyung, you mentioned knowledge augmented.
Yeah, so I think I agree that right now we are in the stage that we see the new power of large models is scaling up and up. But I'm not too sure and when this will continue to go up because the algorithm that we are actually utilizing these days is more or less kind of conventional, that the language model, for instance, actually learn only from the text. It doesn't actually ground on the physical world. So it's learning something like humans, but it's not exactly how humans learn. So maybe there should be some way that this learning has to change. We cannot simply make just feeding in a lot of text data to learn the knowledge. And I think the other things like human thinking, are we trying to make AI just like humans, or are we trying to do something different? For instance, like people like Daniel Kahneman says about system 1 thinking and system 2 thinking. So we are clearly seeing that the large language models are doing system 1 thinking very good. But in terms of system 2 thinking, it's still not good. So if you have just multi-step planning, large language models suffer. So there are some cases that this large language model has enormous background knowledge that is somehow stored in the parameter. So that is good. But if we go into some more step-by-step planning, it doesn't actually work well. So there are certain differences.
So one thing that came up, I think that was it. Oh, Terry, you had something?
Yeah, I just want to add a footnote, okay? So what's remarkable is that it's not just the size that's changing, it's the architectures that are evolving and getting better and better. And it's human ingenuity that is creating those changes. I mean, I showed you the three, there's feed forward, there's recurrent, now there's these large language models, transformers. It's not going to stop. There's much more. And the reason I know that to be true is that if you look into the brain, there are hundreds of brain areas and learning algorithms, right? It's not just one architecture. So there's a long way to go. And you know, it's also true that, by the way, I heard a talk recently about how, where are, you know, new products coming from and how are they put into the hardware. Pick up your cell phone. It's got about 20 processors in it for all special purpose things. And you know, we'll find the same thing will be needed if next generation of these large language models.
Yeah, no, definitely the innovation is very rapid and seems to be increasing in terms of the ingenuity in these models as well as the way we train them and the way the methods that we're using. One thing that I thought was interesting that came up in all the talks today was the role of the humans in interacting with these models. Terry called it the reverse Turing test in the sense that kind of the models are reflecting what the human prompts or what the humans are doing. Johannes had also brought up kind of how the collaboration between humans and computers have been changing due to the kind of the pipeline has changed with these with large-scale models with kind of more one-shot, zero-shot types of learning capabilities. We also heard about JooHyung's work in terms of, again, using large-scale models to interact with humans better, right? To try to better understand their needs and to anticipate what they really would like to do in the physical world. So. Yeah, I mean, what do you think in terms of what are the key things that we should be looking out for in terms of this changing human-machine types of interfaces that are arising? Maybe Johannes, you want to start this one?
Yeah, I think it's, when I think about AI, I always think about it should have a purpose, and the purpose should be coming from humans. And one way to think about the purpose could be that could help us to amplify our intelligence. And right now, the interfaces are, of course, quite crude. You can think about even, as we write our email, a sentence completion is a very crude way of interacting with AI. If you think about GitHub, right, writing a comment is a way of interacting with AI, right? If you go into a search engine and you write a query, that's a way of interacting with AI. And I believe here we've just scratched the surface. If I think about an AI pair programmer, it's somebody who can explain something to me. If I've made a mistake, who guides me towards the mistake. If there are various different ways of understanding my comment, who will help me to disambiguate different semantics of this comment to write actually the correct code. It's also somebody who learns who I am and what I want to do. So in a way, it amplifies my purpose, it amplifies myself. And I believe that in terms of interface, we're just really scratching the surface. I mean, what's really exciting is the creator economy. I'm really excited about the capability of AI for research, right? I mean, we have so many problems that we as humanity face, just sustainability, right? Global warming. And I hope that AI can help us to do our research better and accelerate us in terms of the research that we're doing. Education. I mean, I was at a university for a long time. I believe in education. I think education is one of the things that is so amazing that we humans all can do and that really amplifies us as humans and that everybody can learn. You just have to have the right kind of tutor and the right kind of environment to learn. And again, AI can be, your co-pilot for education and learning. And so I believe that, especially on the interface side, the capabilities are going to increase. And, it looks like right now they're not going to be human-like, right? They may be more task-specific, but maybe very good at many different tasks. And so I think we should think about what are the right kind of interfaces, what are the right kind of workflows, and the right kind of areas where you can really use AI to amplify us as humans and our purpose.
JooHyung, maybe your experience with interacting with?
So we were actually excited to play with a large language model like GPT-3. So we had partnered with Microsoft to use GPT-3 free of charge. And by that process, we actually learned a lot. And I think sooner or later, these technologies will become more widely used. So the end users will just use it normally. And then you'll discover that there are something different from human and AI. You will see that sometimes it works well, sometimes it does not work well. And knowing that when it fails is sometimes frustrating because you expect that doing it like humans, but it doesn't do that yet. So knowing that is actually important to realize certain limit. And in fact, as maybe Terry also said, how you priming is actually important. So the way that you talk to the large language model is also important for having it to talk back to you. So we have to kind of getting better to know about these technologies. So it's actually funny that before these large models, we were carefully designing the architecture, and we have hypotheses, and we test hypotheses using the data and training. But now we just build a big model, and then we have to analyze what is actually going on here. So it's a kind of different way to do research now. And knowing the limit is actually important. And in fact, now these kind of AI technologies will be living with us. So without knowing their capacity, this will affect actually our lives too. So there should be some good education about what these large models can do. And probably it will be getting better and better. But at this point, there are something that it may not do good, and it may actually even affect some part of human activities. So we have to be careful on this side.
And Terry?
Yeah, I resonate with what Johannes said about partnership and also enhancing human capabilities. And in fact, in my book, the tagline was that AI will make you smarter. You know, it's like playing, if you're a tennis player, if you play with someone who's better than you are in some way, that raises the level of your game. And so in all these areas, I can see how that's going to happen, and it is already happening. But you know, I don't think we actually know what the killer application is going to be. Sometimes it takes time. It's only been 10 years, right? In large language model, 3 years. It takes time for people to, you know, explore and try new things, and you know, it's. I'll give you one example from science. I think that one of the biggest applications is advancing science, and in biology, as you probably know, AlphaFold, you know, from DeepMind, solved a problem that many biologists thought would never be solved, which was being able to predict the three-dimensional structure of proteins from the primary amino acid sequence. You know, that was an incredibly difficult problem. No one even knew how to go about it, and DeepMind figured out how to map that into a problem that could be solved by comparing all the existing structures and looking at similarities and generalizing, and that the impact on biology is just beginning to seep in, similar to the impact that the sequencing the human genome had. It's just astonishing, and I see a lot of those turning points coming in the future, you know, in science. And I, you know, this is just a thought. Was thinking about something which elections are here, and you know, in the U.S. And you know, what do lawyers do? Okay, when they go to court, they have to look at all of the previous cases in that area, and they have to then present a case that, you know, that they all point toward a particular ruling. Well, you know, there are these people, the clerks in the back, that are searching through all the, you know, thousands and thousands of, you know, cases and so forth. Well, you know, a large language model could just absorb them all, right? And, you know, it could just basically, it's just, you know, you can talk to it and it'll tell you what you're looking for. It's you know, that just occurred to me a couple of days ago, but you know, there's probably hundreds of problems like that, you know, exactly as Johannes said, that are deep drudgery, and it's going to be taking it off of humans now, so we can do the more creative part of cognition.
Yeah, the interesting thing has been that, you know, in the past we thought of AI as, you know, automating simple kinds of tasks that we humans took for granted. But it looks like these days that the, you know, areas that seem to be, you know, much more high-level human skills, where it's artistic creativity, or being a lawyer, or being a scientist, right? Scientific discovery are now open game for these types of large-scale language models to make an impact. You know, so it looks like, you know, maybe the white-collar jobs are the ones that are being kind of threatened by AI, as opposed to blue-collar jobs, right? Which is what we thought about in the past. So I don't know, where are we still, what is the limit here, right? Is AI going to be able to do the things that we're seeing here and taking, in some sense, replacing a lot of the human effort in this? Or is it always a collaboration that's still needed? Or that are we going to get to these kinds of capabilities that we could basically hand off to a large-scale model? Johannes, maybe you want to address that?
Yeah, I mean, I think, first of all, this is, of course, a question that we as an industry should face jointly. In general, I think, as I said, I believe in human ingenuity. I believe in human capability to learn. All that I see from these models is that their notion of intelligence is very different than human intelligence. It's often very nice and complementary. So I strongly believe in human AI collaboration. And I believe a lot of the tasks that we actually now seem to all agree on, right? The next scientific frontiers, human education, global warming, right? These are all tasks that or quests that we as humanity have been on for decades. And maybe with AI now we actually have a helper along. And that helper actually allows to democratize some of these ideas. It allows us to do some of the things that we would have spent years to organize scientific literature. Maybe it can help us to do that much faster and therefore really accelerate our scientific progress. So I actually am quite hopeful here. But of course, there are big questions that we as the industry, we as a society have to face. And I don't want to sweep these under the rug, but I'm personally actually quite positive. One interesting question here that you can ask along these lines is, what does it mean to get equitable access to these models? Right? As these models become very large, you can think about that an inference now is not like 1/100th of a cent, but an inference is maybe quite expensive because it goes across multiple GPUs or a very, very large model. Right? It might make lots of retrievals and actually might summarize something on the fly for me. Right? It's an interactive request where actually maybe the model even assembles some kind of program to actually do this request. How do we actually ensure that access to these models and access to these capabilities is actually equitable for everybody across the globe? I think is a very interesting question here as well.
Terry or JooHyung?
Yeah, so you brought up the issue of losing jobs, and of course that's what you read in the press, and it is an issue, but I think that's the wrong issue. It's really what's going to happen. We can look at history and look at the Industrial Revolution. So what happened there was that the steam engine greatly amplified human physical power. It used to be the case, 100 years ago, when 98% of all humans were farmers because we needed food. So when you had a tractor that one farmer could basically plow the whole field, you don't need as many farmers. And so what happened was the children of the farmers went to the big cities. They worked in factories. They got different jobs. You didn't have to spend all your time, taking care of the farm. And of course, they worked in the factories that were powered by steam engines, and it created new jobs and new tools and new ways of creating, a different technical civilization. And we're going through the same thing, except much faster. It took 100 years to go from farmers to cities that were now have a tremendous diversity of jobs. Now the problem is that humans aren't evolving as fast as the AI, and that means that whereas before it was generational, and new jobs were learned by the children. Now it's basically people who are still alive have to learn new jobs, right? There has to be new skills. And fortunately, there's something called a MOOC, a massively open online course. And this is tremendously useful because you can take these courses, and there are like 10,000 of these. I have one called Learning How to Learn. It's about how the brain learns and how to improve your learning with Barbara Oakley. And it's 4 million people have taken the course. But this has tremendous potential for being able to help people acquire new skills. So I sort of see there's a completely new revolution that's unfolding, which is an age of information. But we'll see where that goes.
So yeah, I agree with Terry on this shift in the job position. So I think the scaling AI is also scaling human capacity. So there will be some new jobs created and new functionality that we haven't seen before, but with the help of AI, we can make certain impossible things possible. Now, with the current trends, AI is more generative, so it actually generates contents. So for those people who are in that area may be affected by these things. And it's not only about the technology problem. We cannot simply solve human issue with technology only. So the idea is, if we want to generate some Picasso style, some drawing, you can now do this easily with just one sentence. But the same way, you can actually infringe the copyright of the existing human artist who is actually actively working now. That could also happen too. So how do you protect their copyright? Okay, so that is kind of real problem. And as Terry said, we are slow. So there comes the AI ethics and AI regulation, which is actually the reason to back up all these things. But these are slow. It's already happening, and people are using, and somebody says, my colleague Daniel Lee said, is Pandora's box is already opened. So we have to be quick. So it will affect our lives. Like scaling AI is a technology boom, it will also affect our human lives tremendously. So we need to keep up.
Yeah, I think the issue of how do we think about ethics with these new types of models is important. You know, Johannes pointed out that the kind of AI training pipeline has changed, right? From the traditional kind of training set, you know, model architecture, train, and then test set. And there we have developed techniques. We just have started to develop techniques to check, you know, whether there's bias in your training data, whether there's ways of, you know, checking on the test inference side, whether there are things, irregularities in the outputs of these networks that we should be, you know, retraining them into a certain extent. But now with this kind of new workflow, you know, what do we do in order to guarantee that there is no bias in these systems, that they're not, you know, helping, you know, more privileged segments of the community over underprivileged areas. How do we do that now with these new models? So
Dan, this is something that is so important, and we have to face it. We are, for example, there's the NeurIPS meeting that will be held in December, just a couple of weeks from now, is putting a lot of emphasis on this. And it's clear that if we don't regulate ourselves, then the government will come in and do a much worse job. But that having been said, I think that, you know, any technology that first comes on the road, you know, the first cars, I mean, they were claptraps, you know, they had all kinds of problems. It takes all slow incremental improvements. When you start with something, it's always imperfect, and we have a long way to go. But you know, we can see already, you know, the direction it's heading, and we can put in the brakes, and you know, look at nuclear weapons, right? I mean, we were smart enough as a species to stop the race. Maybe, you know, if we can have similar you know, ways to control the technology, that it will also, I hope, be equitable and also be generally available to not just the elite.
Johannes or JooHyung?
Yeah, I would agree with Terry. And I think, again, it boils down to what is the purpose and the goals of these models, right? And as we create these models, what are the principles that we use that underline them? And again, if I think about Microsoft, right, we think about fairness, we think about transparency, we think about inclusiveness, right? We think about accountability and privacy and security in terms of data usage and reliability and safety. And so I think as long as we control then how these models actually behave in terms of really making us as humans better and have the right purpose. And as I said, I mean, you know, the ADA test is a first approach or a trial how to actually use the model itself to prompt the model. I mean, we you know, when Terry was talking earlier, he was talking about Klingon. And the way you talk to these large language models is actually a little bit like Klingon, because what you actually do now is, you know, the models are applied to these tasks out of the box. They have amazing performance with, you know, only a few examples, but what you do is you actually adapt in some sense the task to the model instead of the model to the task, because what you do is in the task is you actually prompt the model with the right prompt. And so while we as humans want to interact with the models in our natural form, the right way is then to actually add the right kind of prompting in front of it. And while this is one of the mechanisms, I think this is a very powerful mechanism to potentially actually guide the model, to have the right kind of behavior. In addition, of course, to having the right kind of purpose, which is to complement us and augment us as human AIs. And so I believe that actually with these very large models, it's really extremely hard to fine-tune them or to, unless you create sort of maybe like a federated model in a client-server way, and then you really nicely adapt these two models so that they fit with each other. Therefore, I believe that we as human AI have to work together to actually make sure that the AI is the right purpose, and then the AI actually adheres to these fairness and accountability principles.
So I agree that we have to be more taking roles. Humans has to be more aware of how to use these models. And when we are working on AI, sometimes we are confronting the issues like, what is actually the goal of this system? Are we trying to make accuracy higher at the expense of ignoring the bias? Or do we want to be fair so that we have to care for that, but reducing the accuracy? I think this is something that we have to think about. When we try to build AI model, we have to be considering the impact of this model. And as large language model, once deployed, is actually hard to retract. It's actually, it will have a lot of impact in various areas. So when we design and implement this algorithm, we have to be careful on this side. And it looks like that humans' role is becoming more important. It's not just AI just helping us. We need to help AI to learn better.
So could I end with a question?
Sure.
Is it going to be easier to change bias and fairness in humans or in AI?
Yeah. Well, maybe we might have a little time to expand on this. And I think one interesting slide that you had, Terry, was that you asked the question whether humans are actually an advanced form of large-scale models. And I definitely know that when I interact with my family, prompting is very important in terms of the responses I get back. That if I don't prompt them correctly, I will get a bad answer back. So what exactly is it that we know about humans, and how we can? Is this study actually telling us more about ourselves to some extent, or our brains? What do we learn?
Yeah.
Johannes, you have something?
Yeah, I think actually, I'm again maybe the optimist here, but I believe that here is where speed matters. So I can ask Terry a few questions to understand his bias and his prejudices, and sort of to get a little bit to understand him better as a person, and what his emotional state is and how he'll react to in various situations. But there's a limit in some sense to the number of A/B tests that I can do with Terry, and that's because he's a physical human being. Whereas with a model, right, you can have models interrogate each other, and you can have a model interrogate itself and try out the right kind of prompting and trying to understand how a model actually behaves. So again, I think this comes back down to that we are sort of, physical human beings who have evolved over, over a very, very long time. Whereas, AI right now is this very new kind of, intelligence that complements us as humans, but it's developing much, much more rapidly. And what this also means is that we can do certain things that may take a long time to discover in humans. We might be able to discover much more quickly, at least in the specialized kind of AIs that we have here right now. And so I'm actually quite positive here that I believe that, we as the tech community will discover problems, and we'll see that these large models will be able to generate bad language, that they will have bias. But I also hope that, and I'm actually a strong believer that we'll generate the right kind of tooling to eliminate the bias whenever we see, and that we can actually eliminate this bias then relatively fast. Maybe the last story that I tell here is that, I worked before I was at Microsoft Research, right? I was a professor, but then I worked for 8 years in product at Microsoft. And one thing I saw, the power in product is the power of speed in software. So you can release something, you can do an A/B test, and you can very quickly see whether something is right or not. And if not, you can quickly go and fix it. And so that's actually the power of models as well. You can deploy a model, you get very quickly some intuition back of how the model is actually being used and whether the model is actually working or not, and potentially even measuring what kind of biases the model has. And in that way, then you can very quickly get data back, and then you can actually react to it. And so again, this is this loop where human and AI work better together, where humans then actually help the model to become less biased over time, and hopefully really go into this long tail that these scenarios don't have.
Last thoughts, JooHyung, Terry? Terry?
Yeah. Okay. So, I think, the area that I think is going to be the most exciting is the topic of personal assistance, that Johannes brought up. And it could be a personal assistant, a lifetime assistant, right? It will grow with you as you make decisions in life. It can help you. For students, it can help debug them in terms of mental blocks, and the potential there is enormous, and it would help. In education, by far the most effective way to educate a child is one-on-one interaction with an adult who is a good educator. Classrooms are very inefficient with 30 people in them. And and people on their own are wander randomly. And so if an AI can get to the point where it understands you personally and your both the flaws and also what your skills are, and what they can mold you in a way that it could be for anybody, right? This will be universal, equitable. I think that's really for me would be the most exciting outcome.
All right, well, I think we're out of time. So I want to thank again all our speakers here today. Thank you for their wonderful presentations and their thoughts. So please give a round of applause to all our speakers.
Next is the keynote by Sebastian Seung, Corporate President of SangHa Research. Good afternoon, Sebastian.
Can I start now?
Okay, can you see?
All right, first I'd like to acknowledge that this work comes from the PhD thesis of Kyle Luther, who was a graduate student at Princeton University. He's a brilliant guy, and this work obviously is due mainly to him. I'd like to explain it to you today. And the question that I'm going to talk about, just for fun, is how does the brain learn? This is not about scale and AI. It's not even really about artificial intelligence. This is an unsolved problem about biological neural nets. It's a fundamental question that's just curiosity-driven basic research. Obviously, there's some relationship to artificial intelligence, but it's really a neuroscience question. So let's start with the backpropagation learning algorithm, which, as everybody knows, and as we've heard today, has had fantastic success in engineering applications. And if we look at the mathematical form of backprop, we can see that learning, which happens through changes in synaptic weights, delta Wij, the change in the connection strength, the weight of the connection from neuron I to neuron J, is given by the product of the activity of neuron I and the activity of neuron J in a separate computation called the backward pass. So every artificial neuron has two activities. There's this A sub I, which is the activity which corresponds to what a neuroscientist might measure in an experiment from the brain, the actual spiking activity of a neuron. But then there's this other activity, B sub J, which no neuroscientist has ever measured because nobody knows what that corresponds to in the brain. It's not clear what biophysical variable inside a neuron might represent this activity of a neuron during the backward pass. And so it's just not clear how backpropagation would be implemented by the brain. Now, there's a long history of Hebbian learning in brain theories. And this is a lot simpler, more primitive kind of learning algorithm. And in this algorithm, the change in the connection from neuron I to neuron J is just given by the product of the activity of neuron I and the activity of neuron J. There's just a single activity for each neuron. There's no backward pass, which is the major feature of backpropagation. And Hebbian learning is in all the textbooks, all the neuroscience textbooks, because it's consistent with a lot of experimental evidence from biological neurons. But sad to say, it's useless today in engineering applications. Hebbian learning has completely lost to backprop. There is no use of Hebbian learning in engineering that I know of, almost none. And so that kind of undermines its plausibility as a theory for how the brain works. If you can't duplicate the functions of the brain with Hebbian learning, then that might be a strike against Hebbian learning. And so I like to say that there's an intellectual crisis in neuroscience. AI is fine, but there's an intellectual crisis in neuroscience. It's kind of like the crisis in physics provoked by the discoveries about quantum mechanics. And that crisis is the following. We have a split into two camps. So some people say, oh, well, backprop is so powerful. The brain must be using backprop, right? Gotta be. We just haven't figured out how the brain implements backprop yet. And there's another camp, kind of the conservative camp, which would say, well, Heb, it really looks primitive. It doesn't have that fancy backward pass of back propagation that enables you to compute a gradient. But Heb is primitive, but the brain is somehow able to learn anyway. And we just need to figure out how that is. And nobody knows yet which of these camps is right. I think either way, the answer could be revolutionary. Doesn't, no matter which camp turns out to be right, I think the actual answer is going to be revolutionary. And I said that this is curiosity-driven basic research. That's true in the short term, but fundamental advances in questions always have some kind of applications in the long term. So you could imagine neuromorphic chips that are able to function in spite of unreliable primitive elements. Maybe understanding how the brain learns would help with that. That's actually a rationale that I heard Jeff Hinton express recently. And some brain disorders might be caused by malfunctioning learning mechanisms inside the brain. If we understand how the brain learns, that surely would have some effect on our ability to understand and treat brain disorders. All right, so I'm going to take the right-hand perspective that somehow the brain learns, even though Heb is so primitive. And I'm going to start by reviewing the history of Hebbian learning. There's actually several decades of this. In the 1980s, people realized that k-means clustering and principal components analysis can be implemented as neural nets with Hebbian connections. And in the 1990s, this kind of work continued with independent components analysis. Actually, you heard from Terry Sejnowski, who was a pioneer in independent components analysis, sparse coding, other algorithms in the 2000s, so restricted Boltzmann machines, denoising autoencoders, and so on. And repeatedly, what was shown was that you can implement these as neural nets, single layer neural nets, with Hebbian or sort of Hebbian looking synapses. And they all learn nice looking features from data. But obviously a single layer net is it's not that complicated. So the problem was, how do you make a multi-layer net? And so one approach was stacked Hebbian learning. So the idea was, let's just pick your favorite single layer algorithm and let's apply it repeatedly. So take independent component analysis, take the output of that and apply independent component analysis again. Take the output of that and apply independent component analysis again. So the hope was that if you stack, you'll get powerful multi-layer nets without backprop. And the biological inspiration was that if you look at all the different areas of cerebral cortex, some people think that it's the same basic circuit. They look very similar in terms of microcircuitry. So the same basic circuit looks repeated inside the cerebral cortex. And this approach is really old. So Fukushima, his neocognitron in 1980, the precursor of today's convolutional nets, that was an example of stacked Hebbian learning. And Jeff Hinton and Yoshua Bengio in the 2000s, they also pursued stacked Hebbian learning. But as we know, this approach was abandoned, and it's abandoned because its performance was really poor. There was a lot of interest, but the accuracy at tasks like visual object recognition produced by stacked Hebbian learning was just pretty bad. And so people gave up. And so what I'm going to talk about today are some baby steps at reviving this approach. In a field like computer science, one of the weird things is that an approach can be dead for 10 years or longer. And if you come back to it with superior computational power, you might be able to make a new start. All right, so let's first do the problem definition. I'm going to talk about unsupervised representation learning. Here's a simple example. As you all know, if you take MNIST digits and you try to naively divide them into 10 clusters using a simple algorithm like k-means, you would hope to get clusters that correspond with the 10-digit classes. But in fact, you're going to end up with clusters that are mixtures of digits from different classes. life isn't that easy, right? So a simple algorithm like this doesn't cluster in NIST digits perfectly. And so you can evaluate the quality of the clustering, just find the best permutation of clusters to fit the labels, and then compute the fraction of incorrect labels. And what you'll find is that roughly half the images belong to the wrong cluster when you're done. So, more precisely here, 46.5% is the error of k-means applied to just regular old image pixels. So the task of unsupervised representation learning is to improve upon that. So with no labels, learn to map every one of those images to an alternative representation vector. And the hope is that those new representation vectors are going to cluster really nicely with k-means, that the clustering error is going to be lower when you apply k-means to them. And here's a picture of kind of illustrating intuitively what we want. Imagine that we have 3 input images. So this is the space of the multidimensional space of groups of pixels. And imagine we have 3 points right here. Each one of these points, let's say 2 of these points are from the same digit class, and one of these points is an image from a different digit class. What we would like is that the same class pairs should move close together. So X and X prime should get mapped to R and R prime, which are close together. And then this is the different digit class. R double prime should be far away from R and R prime. Now, finding this map, F, that takes you to a new representation, it seems kind of trivial. And it would be, except we're not allowing any labels to be used in the learning. So you don't know, the learning algorithm doesn't know which are the pairs of the same class and which are the pairs of the different classes. There's no labels. But the state-of-the-art procedure actually relies on training set augmentation. So even if you have unlabeled examples, you can generate same class pairs just by applying geometric distortions. So for example, if I have a single image of a 5, I can apply a rotation or a shearing, and I can get a distorted version that's of the same class. And so once you generate these same class pairs, you can use backprop to train an output of the neural net to be invariant to those distortions. And SimClare is one of the best known methods that does this, but there's plenty of other examples in the literature, and I've just listed 2 here. And on that MNIST data set, they get between 1% and 2% error. So much better than k-means on the raw pixels. If you learn the right representations, you can get between 1% and 2% error. All right, but I'm going to impose a rule of the game. What I'm going to propose is that no training set augmentation should be allowed, which might seem like it might seem a little weird to impose that rule. But the motivation is that if you're not fixated on vision only, the hope is to find a general approach that works in domains other than vision, and a general approach that doesn't require prior information about invariances. So pure learning approach. And so if you impose that constraint, you can find that there's many well-known algorithms which you could apply for this unsupervised representation learning, but their performance is much worse. So if you look at, on the right-hand side here, you can see that many of these algorithms like GANs or variational autoencoders are going to give you something like 17 or 18% error at this unsupervised clustering task. And so the question then is, with something like stacked Hebbian learning, can we do much better than this? Maybe not as well as the training set augmentation methods, but can we get much better error than this? Can we get a state-of-the-art kind of performance? Okay, so I'll show you a solution with stacked Hebbian learning. And this solution is going to use a so-called convolutional energy layer. So this is just, you got it for stacking, you have to choose the thing that you're going to stack. And so this is a Hebbian single layer network. it's equivalent to modeling an image patch as a mixture of K subspaces of rank R. And you could implement this as a network with a convolutional layer that produces K times R feature maps, followed by a norm operation that collapses those feature maps to K feature maps. That's done for every image patch, not for the whole image. So you're going to get a convolutional structure out of this. And it turns out this is closely related to the independent subspaces analysis that was proposed by Aapo Hyvarinen. And so we're just going to stack these convolutional energy layers so that every layer's input is the output of the previous layer. And we're going to learn each layer and freeze it before proceeding to the next layer. And then we're also going to add some gain control, which turns out to be critical for getting decent performance. So for every one of these K-dimensional feature vectors, we'll adaptively threshold it so that there's some fixed number of winning neurons active. So we'll adjust the threshold dynamically. And then we're going to normalize the feature vector based on its length and also the length of the input to that patch at the same location. And so this is showing you the whole architecture of the network. In between, here's the stacking of multiple energy layers. In the beginning, we'll put in a special whitening layer called convolutional ZCA, that's pre-processing. And then at the end, we'll put in a post-processing layer, which is average pooling. And so, if you do that, the stacking, as you stack the layers on, the representation actually does improve. So we just monitor, imagine that we monitor the clustering error after adding each one of those, after adding each layer of the stack. So we're starting out with this 46.2% error of k-means applied to pixels. But now, after we add a layer every time, we'll measure the clustering error again with k-means. And you can see that the first layer of ZCA whitening, it actually makes the performance a little worse. But when we add another energy layer, the error drops to 23%. If we add another energy layer, the error drops a little bit. And then if we add a third energy layer, the error drops to close to 2%. And so an average pooling helps you do a little better after that. And so this is comparable to state-of-the-art performance. It's not quite as good as if you use training data augmentation, but it's a lot better than a lot of the algorithms that I showed you in the list before. All right, and then the solution that you find actually has interesting resemblances to the biological visual system in mammals. The ZCA whitening is a center surround filter, which is reminiscent of previous computational theories of the retina, which argues the retina basically performs a center surround filtering. It's kind of surprising that here, the whitening actually initially hurts performance, but you can show that the effect of the whitening is to improve the performance of the later layers. So it's an interesting situation where you have to take one step backward to take 3 steps forward. And then if you look at the first convolutional energy layer, it has a lot of similarities to the primary visual cortex. So here's a visualization of the kernels learned by, there's 37 subspaces, each of rank 2. And so there's 2 kernels for each of those subspaces. Okay. And you can see that these pairs of kernels are, they're slightly distorted versions of each other. Like these 2 right here look like shifted versions of each other. And so when you apply this sum of squares nonlinearity, it turns out you get a feature detector that has some kind of invariance to it, shift invariance to it in this particular case. And this turns out to be closely related to models of simple and complex cells in primary visual cortex, specifically Oppo Hyverian and Patrick Hoyer in 2000. And this is just showing you how the representations change as you move through the network. Here's the raw pixels on the left. Here is the whitened representation, which is like the retina. This is layer 1, which is 20, it's sparse, about 20% of the neurons are active. Layer 2 is much more dense. Basically, all neurons are active if there's something in their receptive field in layer 2. And then finally, in layer 3, we go back to a sparse representation, which is about 5% active. All right, so what I've shown you then is that you can get state-of-the-art performance, albeit in a very simple task. And I think the kind of surprising thing is how trivial it is. You know, this unsupervised learning algorithm I just showed you, this Hebbian learning algorithm, it could have been done in the 20 years ago, 30 years ago, and so on. It's very, very simple, and the things, elements that I put together are all known. So what's the catch? Well, the catch, and you know, it's basically the search for the network architecture. That it's the meta learning. So if you just take, well, this is the actual network architecture that we use, which has some number of feature maps and et cetera, kernel sizes and so on. And if you use this network architecture, you get state-of-the-art performance. But if you use the wrong network architecture, you won't. And so basically, now we have the computational ability to search for that network architecture that makes the stacked Hebbian learning actually deliver reasonable performance. It's as simple as that. And so here's the hyperparameter search. We use this nice, Kyle used this nice Optuna software package that uses the Bayesian method to do the hyperparameter search. And over time, you know, you start out with an architecture with not very good performance, but over time, you find an architecture that has state-of-the-art performance. And so we can distinguish them between the learning and the meta learning. So in the inner loop, we have the learning of the network weights by this kind of stacked Hebbian learning, very classic looking unsupervised algorithm. But there's an outer loop then, which finds the network architecture for which that can actually deliver good performance. And we have these meta-learning experiments where we can actually do ablations and so on. So a few interesting things happen. You know, 3 energy layers is good. If you have a 4th energy layer, your error actually goes down. So I don't know, we don't know why, but that's the case. This is showing that if you don't have the whitening, your performance goes down. So it's like the retina is actually helping the subsequent layers learn. This is 1D subspaces, so that's more similar to a class of unsupervised Hebbian learning algorithms that were based on k-means clustering. And so 1D subspaces don't work quite as well. Well, they work substantially worse, I guess, than the subspace learning. And this is just to show you that random subspaces are actually much worse. So the learning is doing something here. It's not just like a random representation actually solves this problem. Okay, so the analogy with evolution, right, is that there's just very kind of weak prior information only inside the network architecture. So in this search process, when a network is born, the architecture is the only information inherited from previous networks. It's the only information sort of where classification performance can be inherited to this new network. And as this network lives and learns, it just gets a single score, which is its clustering error. And then that weak signal is used to choose the next architectures to explore. So there's some analogy here with evolution. You know, in biological neural nets, we have an architecture which is presumably encoded by the genes, and that architecture is optimized by evolution in order to give us the capability to learn in a given lifetime. All right, so conclusion. why did why did stacked heavy learning fail? What I would say is that to figure out how the brain learns, theory is not enough. You can't just make up these cost functions for unsupervised learning and hope they're going to be great. And why might stacked heavy learning succeed now? Well, high performance computing enables us to search the space of these algorithms. So that's just computation has gotten more powerful. And clearly these are just baby steps. The open questions are, can this meta-learning approach generalize to other similar tasks? And most importantly, can we actually make this task work for realistic computer vision data sets, not simple things like MNIST? So I want to thank you all for your attention. And so thanks for listening to this talk on really basic research.
If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. Next is the third invited speech by Dieter Fox. He is from the University of Washington and the Robotics Research Lab leader in nVidia. Hello, Dieter. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. Next is the third invited speech by Dieter Fox. He is from the University of Washington and the Robotics Research Lab leader in nVidia. Hello, Dieter.
Hello. Oh, wait, I have to. Can you hear me? Okay, great. Thank you. Yeah, hi, everybody. My name is Dieter Fox. I am sharing my time at two positions currently. I am a professor at the University of Washington in computer science, and I'm also spending half of my time at nVidia, where I'm leading a robotics research lab. And today I'm going to talk about research in manipulation that I've done both jointly at nVidia and the University of Washington. So the research goal of the lab, especially but also at the university, is really we want to do basic research that enables the next generation of robots and specifically manipulators that can interact with people and solve complex tasks in open-ended environments. So if you want robots to be useful in settings like, for example, healthcare robotics, or robots that are able to help elderly people leading an independent life, robots in industrial manufacturing settings. And these robots need to be able to perceive their environment, interact with people, and also kind of understand their environments and learn over time in order to solve these complex tasks. So today I want to focus on one specific aspect of the work we've done, and that is kind of towards enabling manipulation tasks where the robot does not have knowledge of all the objects in its environments. In order to kind of set the stage and contrast that with what I call model-based robot manipulation, let me just give you one example of what I have in mind by model-based manipulation, and then I'm going to talk and focus on model-free robot manipulation. So in model-based manipulation, what I mean is that the robot, for example, has access to 3D models of all the objects it has to interact with. So in this case, for example, on the left side, you see a robot, and let's say it's operating in a kitchen environment. And imagine this robot has a model of the kitchen, of the furniture in the kitchen. It knows the layout of the drawers and the cabinets, and it also knows the objects in the environment. We can now use computer vision depth cameras in order to locate the different objects and enable the robot to perform manipulation tasks in this environment. Let me just give you one example where the robot actually will put the sugar box that you can see here into the cabinet up here. And what the robot knows based on its planning algorithm, it can fully autonomously determine. The first thing is it has to open the cabinet door in order to access the inside of the cabinet. And then it can plan how to reach now for the sugar box while avoiding, for example, collisions with other obstacles or objects in the environment. And it can plan a path in order to move this object now into the cabinet. All of this can be done fully autonomously. You can see on the right side is kind of the internal state that we are tracking with a camera system. So we track the position of the robot, we can detect the different objects, and because we know the object models, you can see here on the right side also in colored, we have kind of locations of the different object models, and we can plan ahead, for example, how the robot should pick up an object. So the advantage of such a, what I call model-based approach, is that we can perform actually relatively complex reasoning in these systems, and it fully takes advantage of known object models if they are available. Key limitations are that, of course, first of all, in many environments, we do not have access to 3D models of objects. So the robot needs to be able to operate on unknown objects. And it actually turns out that operating under the assumption of known object models makes the overall system slightly more brittle, because the robot kind of compresses all the information into information such as the position of an object. And if the position of an object is estimated with noise and uncertainty, then all this kind of noise and uncertainty also translates into uncertainties in the execution of the robot. So what I want to present now is some examples of the work we've done towards a model-free grasping and manipulation of unknown objects. So from now on, we do not assume, for example, that the robot has models of the objects that it wants to manipulate. And we also do not assume that it has even seen these objects beforehand during training. Let me just give you one example of the kind of setting that we might have in mind. Imagine here's our robot manipulator. On the left side, you just see the external camera view. You can see here is the gripper of the robot, and above the gripper, there's a depth camera. And on the right side, you can see the view as the robot perceives the scene using the depth camera on the gripper. Okay. And now imagine the user would like to tell the robot, hey, pick up this object indicated by the red star. Okay. So now what we would like to do is to have a system such that the robot can use this information along with the perception and solve this object manipulation problem. Okay, so what we need to do in order to do this is first the robot has to be able to segment the scene into individual objects, and then it has to be able to reason about how it can pick up an object, and it needs to also check for collisions because it doesn't want to collide with objects that are in the way. So now let me just give you kind of examples for the different components and how we approach these. The first part is object segmentation. And this is, of course, a well-known computer vision problem. And we've performed different approaches. And the idea is that we want to train the system to segment unknown objects in a scene into individual objects. In order to do that, we can actually generate nowadays very large-scale data sets in simulation. Here you see, for example, one image where on the left you see an artificially rendered RGB image. In the middle, you can see a depth image that kind of conveys the 3D shape of the objects. And on the right side, you can see what the segmentation of the scene would look like. The nice thing is by doing this in simulation, we can control the noise parameters of the generation model, and we also get all the labels that we need on the right side for free. We can now use these labels to train deep networks using different approaches. One of them, for example, is using contrastive learning, where the network learns to take as input the RGB image and the depth image and map individual pixels to a feature space such that pixels that belong to the same object are represented by vectors in this feature space that are similar to each other, and pixels that belong to different objects are trained to be far apart in this feature space. So this approach is called contrastive learning. And I'll just give you one example for what the result of this then is. So here you can see an input image of different scenes. And I hope you agree that these are non-trivial scenes to segment actually. So there's quite some occlusion and cluttering going on. Here you can see what the network that is trained purely in simulation generates in this feature space. So this is a coloring according to a representation of this feature space. And you can already see that objects are kind of have similar internal colors. And then this is also trained to be connected to a clustering algorithm in this feature space. And then finally, we get a segmentation of the scene that looks like this, where the white lines show the contours between the different objects. And then you can see the clustering of the scene. And I hope that this indicates to you that this is actually working pretty well. Interestingly, again, this is purely trained in simulation. And the images that we generate don't have to be perfectly photorealistic. And often what we see in these training scenarios is that you just have to make sure also that you add enough noise to the training data. So now that we can segment a scene, the next thing the robot has to do is to figure out if it knows where there's an object in the scene. The next is to find out how to pick up an object. And we train this also in simulation. What you can see here on the left is a setting where we take the 3D model of an object. In this case, it's kind of a spam can from the YCP object dataset. And we can, for this object, we can now randomly generate thousands of possible graphs, which means thousands of ways how to place the gripper relative to the object. We can now feed this into a physics simulator, okay? And for each of these grasp poses, we can check if when the robot closes its gripper, if the object stays within the gripper or whether it moves out. So the gripper is slightly shaking the object, as you can see. And if the object stays within the gripper, then that was a good grasp pose, and otherwise it's not a good grasp pose. Okay, using this process, we can now take an object and we can generate many, many different successful grasp poses for this object. And all of this can be done pretty efficiently using, of course, parallelization and parallelized simulation on a GPU. So now what we have is for this object, we have a sample set of good grasp poses, and we can do this for many objects as well. In this case, we use the ShapeNet dataset, which has almost 9,000 objects. And for every object, again, we can generate grasps using the simulation that have a high chance of success. You can see this on the right side. These kind of green lines indicate the gripper poses that are successful on these objects. And here this just illustrates the scale of the data set, okay? So now that we have almost 9,000 objects, each of those is annotated, in this case, actually with 2,000 different grasp poses. We have a large scale data set annotated with a distribution of these grasps. We can now feed this into a deep learning technique and train a deep network to replicate and generate good grasps. Let me just give you one example here. We have different techniques for this, but one is, for example, we can take an object from the data set and we can render a view onto the object. So you can see here a point cloud of the object. So this is importantly, this is not a complete model of the object, but it is rendered according to, for example, how a depth camera would perceive the object. So we have occlusions here as well. And now we can train a deep network. In this case, it's called a conditional variational order encoder that generates, based on that point cloud, it generates different gripper poses that match the distribution of the successful gripper poses in the training data set. So this network replicates the distribution of a good grasp for an object. Importantly, we train the same network on all 9,000 objects, which means the network somehow has to learn kind of in general what it means to be a good grasp. So it cannot just memorize all the 9,000 objects. It has to learn more general properties of good grasps. We then add to this, and I'm not don't have time to go into the details here at all, with an additional network that just takes as input the point cloud of the object along with the point cloud of a gripper that is sampled according by the grasp sampler on the left side. And this network is discriminatively trained in order to distinguish good sample grasp from bad sample grasp, just in order to refine the results that we get in the first stage. And we can, since this is a deep network, we can actually differentiate through it and iteratively refine the pose of the gripper in order to have a highly successful grasp generated. After this has been trained on simulation data, I show you here results of how this works on real-world objects. So two things to note here is, first of all, this system was solidly trained in simulation, and it worked actually right away on real-world data using depth camera. And the other important aspect is that the objects that we see here were not in the training data. So the robot truly learned to pick up kind of relative, as you can see, standard objects very well. Okay. So now the robot can pick up these individual objects from a table, let's say. But this is just individual objects. So if we want to extend this to the setting that I showed you initially, where there are multiple objects in the scene, we extended this whole training pipeline, and I'll just give you a high-level idea for how this now works. So imagine you have this cluttered scene and you have this input observation. And let's assume the user indicates that the robot should pick up object number 3. The segmentation that you can see here is performed by our trained segmentation network. So now we can crop the point cloud around target object number 3, and we can use the grasp sampler in order to generate good grasp for the target object. Okay, so this is just the grasp sampler that I described on the previous slide. And now what we can also do is we can look at the complete point cloud and check which of these grabber poses are actually in collision with other objects in the scene, because the robot might not reach these different grasp poses. Okay, and in order to do this, actually it turns out that it is better to train an additional deep network that performs collision checking rather than simply checking collisions on the observed point cloud, because there are various occlusions in the scene. And it turns out that we can train a deep network to reason about even occluded areas in the scene. Okay, so now this whole system can be applied to solve the problem that I just indicated to you at the beginning. Again, let's look here at the scene where the robot on the left side observes these objects on the table. And the user indicates that the robot should pick up the white coffee cup. First, it segments out the different objects, and it can now generate grasp for this object. And it also evaluates how much the other objects in the scene interfere with the grasp poses, which means how much they are in collision with the grasp poses. In this case, it turns out that none of the grasp for the white coffee cup are actually accessible. And in this case, the object here segmented out as the red object is the one that is mostly in collision. And what the system now can do is it can say, well, I better get rid of this object in order to try to access the white coffee cup. So now we can just revert to the same task and say, okay, the robot needs to pick up this object. And it runs the same pipeline. And in this case, it actually determined that it can pick up this object. It can move it out of the way. And then afterwards, it goes back to the original scene and can now determine whether it now is able to pick up the original target object, which is the white coffee cup. And in this case, it can do so. Again, what's interesting from my perspective here is that at no point did the robot actually use an object model in order to reason about the scene. Everything was fully operating on the raw point cloud of the scene. Whereas during training, of course, we did use many object models that we simulate on. Okay, this was just one example. We've done some more work also on semantic reasoning and more complex settings. But I want to move on to one other way of training a robot to perform manipulation tasks without access to object models. And this is work that my student Mohit Sridhar, in collaboration with the nVidia lab, worked on. And here the idea is to use what we call option-centric manipulation and leveraging language instructions for these. And you might have heard of work in, for example, large language modeling like clip networks. And the idea of this work was to combine an existing work, in this case, transporter networks, with language capabilities in order to enable kind of manipulation training with language. So transporter networks was work that was introduced by Andy Zhang and his colleagues at Google. And it is work that operates on top-down manipulation task where the robot picks an object and places the object, and it operates on tabletop scenario. This is very powerful system. However, it comes with the limitation that it cannot generalize to new tasks because every scene has to be trained individually by a specific network for this task. So it doesn't generalize at all. So this brought us to the idea that we can connect that with CLIP, which is one of these large-scale pre-trained language and vision models. The advantage of CLIP is that it's trained on very large scales of internet data and is extremely robust. However, it is not trained on manipulation kind of data. And it turns out that the resolution of the embeddings it generates are not quite good enough. So the idea was here to combine these transporter net and CLIP together to get the benefits of both, because CLIP has this strong language understanding incorporated into the network. I'm not going to go into the details on how we did this in the network. I encourage you to take a look at the paper that was published last year at CORE. I just want to give you an example for how this now works. So for data collection to train the robot to perform a specific task, what all we have to indicate, let's assume we have, you can see my mouse here, the stacking task. Let's assume you want to stack the blue block on the yellow block. What you have to indicate in a top-down view of the scene is where the gripper has to move down in order to pick up a block. This would be the red line. And then where the gripper has to move in order to release the block, which would be in this case the green line. So just by indicating two gripper poses, we can specify a large set of tasks. And then using, of course, training with deep networks, we can train a policy so that the robot can perform these tasks on slight variations of these. What's really interesting here is that all the tasks that you can see here were trained with a total of 179 examples. So collecting the training data for these tasks was actually relatively easy. Let me just give you an example of what the robot can do now.
Put the orange block on the blue block.
So here the task is put the orange on the blue block.
Put the red blocks in the green bowl.
And in this case, because we are using language, we have a single network that is trained to perform all these tasks jointly. So we did not have to train individual networks for individual tasks. So the network really kind of leverages the power of the language understanding.
Pack the scissors in the brown box.
Okay, here's another kind of task. So here the robot has to really recognize or learn what it means to move the rook one block forward. So it has to reason that, oh, this is identified by the different fields on the chessboard. And you can see even if the chessboard is moved, the system works pretty robustly. Here's another task. And this is an example of a task that you cannot specify using, let's say, segmentation and object recognition and things like that, just because there are no individual objects that the robot reasons about here in this scene, right? It's much more like a task on kind of this general granular media. Here's a final example, like picking up cherries. And again, all of these tasks that I showed you were trained with a single network from less than 200 training examples. So here, the tricky thing is that the robot has to pick up the cherries actually at the stem in order not to squeeze them. I don't have time to go into this, but in the upcoming call conference, I encourage you to take a look at the paper. We extended this work to full 3D reasoning so that the gripper poses are not only designed for top-down, but it is a full 6-dimensional gripper pose space using transformer networks. Let me just show you one example here. And this was also trained from a relatively small number of examples. So you can see that the network is actually doing relatively complex reasoning in order to do this. All right, with that, in the interest of time, I'm not going to go into any specifics on the simulation side, but you can see here, this is just an example of a real world kitchen and the simulated version of this kitchen. And I hope you agree that it's actually not trivial to distinguish the real world from the simulated world. And I think this is just an indication that I believe there's a huge power in training robots in simulation, simply because simulation is becoming more and more realistic, both visually and from the physics side as well. Here's one other example on actually simulating industrial grade, very tight, contact-rich manipulation tasks. In this case, it's actually nut on bolt tasks, which we can now use to train, for example, reinforcement learning policies in simulation for these kind of tasks. Feel free to ask me questions about this later on. I just want to kind of give you an idea of these kinds of work. Another line of research is on deformable objects, which are important, of course, for industrial tasks, but also for food manipulation tasks or granular media, as you can see here on the lower side. And here the goal is to have simulations that are as realistic as possible. Okay, with these examples, I want to conclude. And what I talked about was that on the one hand side, for manipulation, if we have explicit object models, which I showed you at the very beginning, then of course these enable us to do relatively complex reasoning about different manipulation tasks and perform long-term planning. The problem is that, of course, in many situations, the robot doesn't have object models available, and this kind of reasoning also comes with some brittleness with it. I think there's a huge benefit to learning to operate in the raw point cloud data rather than a more model-based approach. I showed you examples that even with this system, we can perform kind of object level reasoning, even for unknown objects, and we can train these systems in simulation very well. On the last part, I also showed you these action-centric representations, which also allows us to kind of combine raw image data and point cloud data, even in this case with language instructions to learn from demonstrations. And I think on the long run, again, these new simulation tools that we see coming up more and more are going to be very powerful, I think, in order to train robots, but also for benchmarking and for developing in order to enable these kind of very highly complex and flexible robot systems. With that, I'd like to, of course, thank all the team that contributed to this and the great collaborators we had, both at the University of Washington and also with interns. And with that, thank you very much for your attention.
Next is lightning talk by SangHa Kim of Samsung Research. Hello, SangHa.
Hi, my name is SangHa from Language Voice team in Samsung Research. I'm happy to giving a lightning talk here, and thank you for inviting me. And Today, I would like to introduce our Samsung Research machine translation technology and services. These days, we are connected with many people in the world, and we communication with them. And every day, we watch the global news on the TV, and we consume a lot of the contents on the internet. Machine translation technology can help us to understand other languages, and also it can help to deliver information from the different country efficiently to us. Plus, we can communicate it with the hyperscale, the AI model, even though this model trained mainly in English using the machine translation. We hope the machine translation can help people to enjoy the global activity in the Samsung product and service using machine translation. Our teams have researched and developed the machine translation solution, and we have provided the translation service in Samsung Group since 2013. Many Samsung employees every day use our solution through the Knox Messenger or the Work systems. Also, our teams support the commercial services in Samsung product, such as the Bixby Vision or the Samsung Internet. Now we open the SI Translate service, that one. Yeah. Because we want to communication with our users directly, because we want to listen to users' feedback, and we improve our solution using their command. Our teams are interested in these kinds of machine translation topics. Today, I will introduce some of them, and the technology I will introduce from now on are the research that conducted by Samsung Research and the Samsung Overseas R&D Institute in China and Poland. Also, I want to take opportunity to thank those of you who would be happy with us. The first item is the multi-domain translation. In the real world, the machine translation services are used in the different domain. It means the terminology and the styles are totally different for each domain. But if we develop the separate model per each domain, then I think that the development cost will increase inefficiently. So we adapt the mixture of expert transformer for the multi-domain translation. We'll replace some part. We'll replace the feed-forward layer with the mixture of expert layer. Also, we added the domain discrimination on top of the transformer encoder part. We can activate a domain expert using the domain discriminator. Also, we adapt the target terminology annotation for the terminology translation. We want our model learn how to copy and inflect the target annotation into the target sentence. In this way, our model performed well in the biomedical translation task in WMT 22. Second is the on-device translation with the model completion and the inference, the acceleration. In the model side, we adapt the binary code quantization. This approach is based on the non-uniform quantization. We convert the floating point matrix into the multiple binary code matrix. We can compress our model more than 10 times. In the engine side, we apply the BQGEM, the kernel, in the engine. In this approach, can accelerate the matrix multiplication with the lookup table. We apply these kinds of a method into our on-device translation. You can see the left result. We already our approach on the mobile. That is the result comes from our on-device result. The translation quality is good. Also, we are developing the HTML, the inline the tag annotation model for the browser translation. Maybe you can experience that things. You can maybe see that this solution on the soon our mobile. The third one is the end-to-end speech translation. End-to-end speech translation get the voice input and translate the text directly without the speech recognition. This model have several benefits, such as we can reduce the error propagation and the latency. Also, we can make our model robust against this fluency. We try to make a simultaneous translation too. We apply the monotonic attention into our model. We improve the policy, lead or the light policy with the external language model or the accelerate the simultaneous translation model task. We also try to not only for the algorithm point of view, also we data point of view too. We reorder the chunk-wise the target, the text segment, and then we refine the target expressions using the non-autoregressive the translation model. In this approach, we can generate the simultaneous style data. You can see our demo on our language voice team booth today. This page is our vision. We want to make the user-centric AI-powered translation service with the advanced machine translation technology and the user's feedback. We want to improve our model and make the better result with your feedback or your opinion. That's the reason we opened the SR Translate service. And would you join us in making better the machine translation service? We invite you to our service. We're waiting for your feedback, and we want to improve our performance, and we will be able to repay you the innovative service. You can access our site using the QR code, or you can access the type on the URL, translate.samsung.com. Thank you for listening.
Next is the first invited speech by Seungwon Hwang. She's a professor at Seoul National University. Good afternoon, Professor.
Okay, hello. Thanks for the opportunity to share our recent findings towards the direction of robustifying NLP beyond scale. I'm Seungwon, I'm a professor at SNU, and I'm speaking on behalf of my co-authors in the photo at SNU and also at Microsoft Research and Naver. Okay, why are we interested in NLP task? There were so many interesting examples from SangHa's talk, like translation, which enable us to communicate overcoming language barriers. So NLP helps human-human communication and collaboration and human-machine cooperations. Another example is when you are communicating with human across expertise level, like me talking to medical doctors. It would be great if NLP task can simplify or note-take our conversation to help communicate better. And my students use automatic grammatical correction to collaborate with me better. And then another example is NLP task helping human to collaborate with machine better. A good example is code generation, which appeared in lots of talks in the morning, where you can just specify what you need, and then AI model generates C, C++, or Python code, which is too good to be true, which will significantly reduce or eliminate what software developers are doing. And then there was Professor Fox's talk talking about robotics, where goal-oriented dialogue can help us to control like robots or AI speaker better in our natural language. And I also see question answering or web search as a sort of NLP task mediating us to have intelligent and natural access to a large amount of data stored in computer. And it is exciting time to work on those tasks because we are achieving human level accuracy in many of NLP tasks. So this graph on the right-hand side shows that the MNIST from the Sebastian's talk is blue line, which has started around year 2000 and which took about 15 years to reach human level accuracy. Meanwhile, those NLP tasks are the last three, which started rather late, but it achieved human level accuracy within just a few years. So I want to give you one slide summary of what happened in this magic 5 to 10 years, recent 10 years. There were two breakthroughs. Let me call it NLP 2.0 and 3.0 for simplicity. So NLP 2.0 is this Swiss Army knife, which can be screwdriver, which can be wine opener. Just like that, if you want to build a code generator, you can feed lots of input X, natural language, and then the computer code output that you desire as a human annotated training data, then your Swiss Army knife will be code generator. Then you can feed this same knife with X and Y, which is translation pair, then it will create a translator, just like what SangHa presented in the previous talk. And then many talk already show the inside of Swiss Army knife, which is these days mostly transformer, which will encode your input into a vector, and then it will be trained to be decoded to generate the desired sequence. Or you can use this model for classification tasks. For example, for this natural language and code matching, we can also pose it as a classification task by pairing natural language and code as a pair, as an input, and then ask them to classify whether this pair is equivalent or not. In this case, you can skip the decoder part, but more or less we are using the same model. So let's say that's NLP 2.0. And then there are large-scale language models that every talk is featuring, which is Elmo, GPT, BERT, pre-trained language model, or I will call PLM in the talk. And then I want to point out that this language model, in essence, is just Swiss Army knife. The only difference is that instead of being trained by human-generated task X and Y, it is trained by automatically generated training pairs for self-supervised task of masking out some word and then trying to predict it back, for example, as a classification among all possible words as classes. So since it is automatically generated, you can generate virtually infinite amount of training data out of unlabeled corpus, and you can train very big models. So that's how big language models work. And what is the good news for us? Because it is known that we can borrow this pre-trained encoder for example, making my code generator, and then I will get performance boost for free just by borrowing this pre-trained encoder, by transferring knowledge from language model. So this graph shows that simple model, which is shown in green bar, with borrowing the pre-trained encoder, will suddenly outperform more complex state-of-the-art, which means that with this combination of NLP 2.0 and 3.0, we can build human-level NLP models with relatively low code, small amount of code. Okay, so that's where we are, but if you think of it, we can even throw away Swiss Army knife and then directly ask language model to create code for us. So this is actual GPT generation, where we can show a few Q&A example of what human needs and SQL query, and few pair like that, and then you just directly ask what you need, and then create a big magic mask, because language model is trained to fill whatever the mask is, and it will fill the computer code for you, and then it also works surprisingly well, but not perfect, because if you are familiar with SQL, then there are a few bugs. For example, they are looking for the person with the highest salary. That salary cannot be higher than max. It should be equal to max. So there is a little bit bug there. And then if you look into the last query, you should join another table to look up the user ID of Satish, but they just hallucinate his user ID as 1, which may or may not be true. So, but it is a good initial point if you are a developer. Maybe it is easier to fix here and there than writing all those code from scratch. Okay, so I spent first 5 minutes, and it looks like everything is fine. You can build NLP, human-level NLP models. Then what is the problem? And then I want to spend the rest of my talk talking about robustness. There are lots of robustness issues. People say kids say the darndest thing, but we know that pre-trained language models are even worse. They make so many toxic comments, they create misinformation and disinformation, and so many commercial chatbots are pulled out of services because of bad generation. And then if you look into specific tasks, those task accuracy is also exaggerated, just like this math example here. If you're dividing 16 by 64, 1/4 is the right answer, but this is wrong reason. So if you are solving the problem like this to get it right, eventually you will not generalize when numbers change. So what should we do to make models more robust? To motivate, this is natural language translated into SQL examples. And in order to answer this question, actually, query should look at the blue box satisfying the condition of SB less than 14. They should add it up, 5 plus 2 plus 7, to get the answer right. So AI model gets it right, but if you ask AI model to explain, then we find out that their reasoning is wrong. So in that case, what we can do is that we can add objective. So originally, we usually compare machine predicted output y hat with the ground truth output, but we add another red box term comparing machine explanation with what the supposed explanation. So with that, the table here shows that both the rationalization and the answer quality will improve, which is great news, but it doesn't come for free because now our annotation of x, y should be extended into x, y, z, where z is blue box. But in this problem, we can get this information for free from database parser because we know the SQL ground truth SQL code, so we can identify where the intermediate result should be. So I will spend the rest 10 minutes of the talk trying to convince you that we can robustify training by extending x comma y into x comma y comma z. But this z can come for free with lots of sources like database engine, as in our previous example, or search engines, or game engines, or program parser, and then to provide AI model important new dimensions such as causality, evidentiality, and so on. Okay, so let's start with causality, which was the main topic in day one. Okay, so if you want to train AI model to classify review, this is typical X and Y you provide to AI models. So you show review and then say this is positive. And as a human, we know that the word Spielberg should not be causal to predict this review as positive. Even though he's a good director, he may make a bad movie one day, or even though his movie is good, some people may not like it and then still write bad reviews. So we know that, but without explicitly teaching them, machine models often think Spielberg is a causal factor because they are exposed to mostly positive reviews when this term is around. So for that, we need 2 extra data points where you change wonderful into bad and teach model that this change will flip the label, or you change Spielberg with Bong and then show the label stays the same. So it is like our current annotation is 2-dimensional, but by adding extra annotation, we create new dimension so to help machines to distinguish Spielberg and the wonderful as one being causal and the other not. But again, the point is that this annotation can come for free. And then what we can do is that for every review, we can identify a label preserving perturbation, such as, for example, masking this in the blue box, perturbing this movie, that movie, his movie, and her movie wouldn't change the semantics. So the representation of this masked sentence will represent a group of label preserving perturbations. And similarly, we can build the 3D annotation of potentially label flipping perturbation, which is green box. Then we can have this causally contrastive objective of pulling together representation of input review with the label preserving perturbation while pushing away from the label flipping perturbation. And our recent finding from our recent research, we find this helps to enhance the robustness. And another is, in addition to X, Y, you may want to annotate evidence. So this is work in collaboration with web search engine, where they usually use query and the relevant document pair for supervised signals. They can get it from your clicks because you ask for query and then you tend to click relevant documents. My proposal is that, well, when we are training representing document for ranking, in addition to this X, Y, maybe we can identify which terms explain the relevance of this pair. Again, instead of getting this from human, we could get it by reverse engineering the neural search rankers. And with this additional information, we could enrich document representation, and then we could save document indexing for commercial level search engine with 10-fold and the 3-fold decreases in terms of latency and memory footprint. Another idea is we can also distill relevance labels from the search engine. For example, if you think about your clicks, you are not clicking all the relevant documents. You click one of them, you get your job done, and then you leave search engine. So your annotation is always partial. So there is well-known technique called pseudo-relevance feedback, or PRF, which is assuming search engine is perfect so that their top 3 or top K are guaranteed to be relevant. Then you can use this pair as if it is positive annotation, pseudo-positive annotation. And usually, lots of search engines are using this technique at query time after your query is given. And with what I explained in the previous slide, we could bring this to the training phase so that we could apply that for all the query in the click logs to augment positive and negative annotations. That's one possible use. And another important signal is evidentiality. It is distinguishing whether the evidence is there or not. So I want to illustrate with this question and answering scenario, where question is which country got independence when World War II ended, and there is passage where you are supposed to find answer spent there, and the right answer is Korea, and most AI models will get it right, but with wrong reason, because this passage doesn't have complete evidence to conclude Korea as an answer, because we don't know whether 1945 is when the World War II ended. So what we want to teach to AI models as a z-axis is being able to say, I don't know, or I don't have enough evidence, when they don't have enough evidence, instead of guessing because they asked for a country and then Korea is the only country mentioned in the passage. How about going for Korea? It worked this time, but if the passage had names of 3 countries, the precision will go down significantly. So how do we teach that? Red box is our typical training resource where each question is paired with passage that has both answer and evidence. But our proposal is that training should include answer negative, which has no answer, or evidence negative, which may have right answer, but doesn't have enough sufficient evidence. So we can perturb existing annotation to include evidence and answer negative sets. And then what we can do is that here the red box is the behavior. When QA model knows the answer, they predict the beginning position and the end position of answer with highly skewed confidence. But the problem is that the current QA models, they show the same behavior even when the case negative evidence case. So what we teach is we decorrelate behavior for evidence negative set, or as shown in the left-hand side, we enforce distribution to be close to uniform when you are not confident. Okay, let me just skip compositionality for now, and I'll come back to that if I have time when in the panel. I want to use the last 7 minutes talking about generation. So far we have talked about the typical X, Y supervision can be augmented by other models and other tools to include interesting new dimension Z, which could be causality, evidence, evidentiality, and compositionality. And my proposal is that generation maybe should be similarly input augmented. But here the figure is not coming from my work, but from Google, suggesting that, well, instead of just generating directly, maybe we can invoke external tools and then squeeze in their result for a more robust generation. So if you think about your HTML web pages, you think this is text, but if a lot of time you are sending SQL query to database server and get the answer result, and then they plug it in to create HTML text. So similar idea. So the example in the left-hand side shows that PLM generation sometimes invoke external tools like calculator, even though we know language model can add 2-digit math pretty well, but calculator is perfect, so they invoke it and then generate it. Alternatively, on the right-hand side, you go ahead generating imperfect, non-factual version, but at the same time you use external tool, non-parametric tool such as search engine to find attribution report, and then plug in the factual fact to revise. So why not we consider this kind of model augmentation or interplay for generation? So toward that direction, I worked on code completion problem, where of course we can mask out the remaining part and ask for parameterized generation, but at the same time, we can use partial code to look for code segment, and the generation can consider both of them for much more robust generation. And another important fact is that facts are evolving. So your language model should apply new facts, new president elected for a country or for a company. Then what should we do? Maybe you should retrain the whole language models, but then there are primary efficient way to do it by applying adapter, by applying only a small amount of parameter, you can apply new facts. So that's good news. But if you look into it, then if you apply this new patch, you deal with new fact better, but sometimes you forget the unchanged fact. So it affects what you used to be good as well. So better idea is you keep the language model and the adapter separately, and then train a switch based on evidentiality to decide whether to apply adapter or not in this case. But you can straightforwardly extend that to consider multiple adapters, multiple fact patches. And sometimes this patch can be coming from knowledge base, knowledge graph, other sources, other heterogeneous sources. So you can think of this evidentially switch, deciding which adapter to apply. And that might be a better way to generate in a more robust way. And then lastly, I'm looking into generation for robots, text-based games, and code generation as well, because it is a unique place where what you are generating has a consequence in the world. Your generation, just like what we saw from Professor Fox's talk, what robot is doing is changing the world, so your generation should keep track of what's changing to ensure you generate valid actions. I think even for genetic language models should do that, I think, because, well, language model say same thing over and over, like redundancy, or language model says some conflicting things. I think because they are not treating language generation as something with confidence, and then they are not tracking it. So, for example, I share that I'm a professor. It didn't change much, but there are like several hundred people know this fact. If I'm keeping track of that in my language generation, I wouldn't bore you by saying over and over again that I'm a professor, or I will not share a conflicting fact. So I am interested in these text-based games. Text-based game is sort of text version of robotics, where observations are given as text description, and then you generate action that should be parsable and then valid for underlying text-based engine. So your generation has a more difficult objective of not only being plausible, but you should make sure it is consistent to all the changes made by prior generation and also the underlying engine. And maybe this component is also relevant, not only for solving games well, but also for genetic language problems. And I'm not the only one thinking this way, and there are some work from CMU where you fine-tune not the generic language model, but code language model for language task for a better result. Okay, so my point is that if you generate action, then there is a consequences that if you put the wire down, you no longer have wire, so you shouldn't put wire down again. So we create BART, actionable word model BART for that purpose, which generate based on conditioned by template, and then templates are retrieved based on based on the current states being managed as a knowledge graph and also the prior actions. Okay, so I have 1 minute to conclude. Deep AI models are achieving superhuman accuracy on NLP tasks, but I'm still not using that to give a talk on my behalf or answering your question from Q&A board. All my answers are from myself. Why is the gap between those task accuracy and our perceived accuracy? I think we should consider more about how to generalize better, how to make it more robust. And then there can be many directions, but the one direction I share today is enriching the alignment between human and AI. Just X, Y training we used to, and then just one-time generation that we used to, maybe we can make it more interactive for robust-defying fine-tuning and PLM generation, and it may not cause too much human annotation. Okay, my time is up. Thank you for your attention.
If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. Next is panel discussion. Once again, Daniel Lee will moderate the discussion. Nice to see you again, Daniel.
Joining us, I first want to thank our speakers, Dieter and Seungwon, for their excellent presentations. I know it's getting a little late in Seattle for Dieter, so I really appreciate his time and joining us online. Yeah, so it was great to hear kind of how large-scale models and these new technologies and architectures are being used, in NLP as in robotics. I think the first question I wanted to raise was, the idea of models. Right, so what we heard was in robotics, Dieter mentioned kind of the conventional way in robotics was to use models, 3D object models, doing pose estimation, doing kind of path planning, and he showed that kind of, going away from that, kind of embracing uncertainty and training things kind of in a more general fashion leads to better accuracy. I think something similar has happened in the NLP community, where kind of traditional NLP approaches, where you do, word parts of speech tagging, semantic parsing. Those things have all gone out the window now with these new technologies, where you're just doing these large-scale embeddings, essentially, to do kind of simple predictions. So we're going forward. What is the role of models now with these kinds of machine learning techniques now? Where do we build in models? What do we think? Or do we change the definition of a model that we have to use? So, Dieter or Seungwon, you want to?
After you.
Dieter, yeah, could you comment on that? Yeah, you really contrasted the two approaches there.
I mean, in some sense, it depends on how we view models, right? So, for example, if we train a deep network to do a certain task, then somehow it also has an internal model, right? It's just not the kind of explicit models that we are used to. It's more in the parameters of these of the network. Or many of these networks they generate embeddings or have kind of bottlenecks. And these embedding vectors that you also see, of course, in language models, these are kind of models these systems have, right? And if you think about also these very large-scale transformer systems that we see that are so successful in language and in vision, that also these kind of trained systems, they are performing internal kind of reasoning that some people, I'm sure, at some point might extract some relationships to, for example, grammars and things like that, right? So I believe there's a lot of kind of implicit model reasoning going on. And specifically regarding robotics, there's various efforts now going on where people are trying to see, can we replicate the success of these large-scale, what's called foundation models in robotics. So far, we've seen some early kind of indications that might be possible, but I think we still have a long way to go, just because in robotics, we need compositionality, we need a strong 3D understanding of the scenes a robot has to interact with. So I think we're just at the beginning of this, but I'm very hopeful that I think at some point we might have some kind of foundation models for, at least for something like robotic manipulation.
One follow-up on when you showed the connection to the language with your language model, was that mainly just as an interface for kind of human interaction, or did you try to use aspects of the large-scale language model as part of the kind of internal representations for the robotic task? What would you say?
In network, actually, yes. So on the one hand side, of course, there's the reason about the interface, but one interesting aspect, because every demonstration that was given to the robot came with kind of a language description of that task. And that enabled the network actually also to then, first of all, disentangle these different demonstrations so that one network could actually learn all these different skills because it can now train them conditioned on the language input. And what we also saw, some examples where some kind of transfer where, for example, if in one task the robot would learn what green and red means, a green block or red block, then we saw that actually that information partially was transferred also to a different task where a red block could suddenly be used in a different context or something like that. We don't see the strong compositionality that we want to see from language, but there have been some follow-up works where people are pushing this further on.
I think I agree with Professor Fox that the models are, even in model-free embeddings, models are internally and implicitly there, and then there are many evidences probing those pose or other like symbolic structure from those representation, but not sufficiently sometimes is what's the problem, I think. Maybe because data is not extensive enough, or maybe we should use, well, data is just some observation snapshot, and maybe we need some kind of experiment or simulation, which I think is why people are discussing causality, alternative cases beyond what's been observed. So, but model is like mathematical equation to me, and then data is some observations, and then with experiment, I think it can be even close to represent model more clearly. And I guess many researchers are going toward that direction. Model with the convenience of model-free, but with the power of models in an implicit way.
Yes, but then I guess the more you rely, the less you rely on any prior models, then it seems like the needs for data starts to go up. And I think what we saw was, you know, being able to use large corpuses, or in Dieter's case, simulation to kind of generate a lot of these examples that you can do contrastive learning with, or, you know, other types of self-supervised types of ways of using that data in some sense. So maybe, yeah, what is, you know, the role of simulation, or role of being able to do these kind of more generative types of things to train your systems? You think that's critical?
Yeah, that's one of the hot discussions right now, right? Like where does the data come from to train, let's say, large-scale models in robotics? Because we don't have the benefit of all this nice, for example, text that is on the web that is already somewhat curated because it was generated by humans, whereas we don't have any kind of, let's say, annotated robotics data. So there's people who are trying to learn kind of models from, let's say, YouTube kind of data. And I think ultimately I can well imagine that can get us reasonably far. What we are trying right now is more investigating, as you mentioned, how we can leverage simulation for that. The advantage of simulation in this context is, at least if it's an environment that we can have a pretty good understanding about it and model well. So for example, rigid objects, and imagine, for example, in a kitchen type environments where you have doors and drawers, and you want to train a robot to perform manipulation tasks. That is a domain where I hope that, for example, we can actually procedurally generate a huge variety of different environments, just thousands or millions of them. And what's nice is that in simulation, we have access to perfect ground truth information. We know every object in the environment because it's simulated. We know the shape, we know the weight, which means we can use actually traditional model-based techniques to generate training data in simulation to solve tasks that we cannot solve in the real world yet. but we can solve them in simulation. And then we can use that data to train, to replicate that with, for example, deep network type techniques that then can operate, for example, from raw observation data. So there are these techniques, I'm sure you heard of, like distillation and things like that, right? Where you just train your network to replicate the kind of behavior that we can generate, but only using, for example, simulated camera information and not privileged information from the simulator.
But there, you know, the concern would be, you know, domain shift, sim to real transfer. It seems like in your examples that you were able to overcome a lot of these, you know, even with granular media or those kinds of things. Could you comment on what is that still a big issue, or how you overcome those issues?
I think that is the big elephant in the room, is kind of the sim to real gap, right? And so in order to address that, of course, what we need is, first of all, we need realistically looking simulations, but we also will need sufficient variety of data, and that will require large assets, right? How can we generate environments that have the variety of objects in them, and also the visual appearance that is randomized sufficiently well? So how far we can scale that is still an open question. For these kind of tasks that I showed today, when it's about picking up an object, and also in clutter, I think we've been pretty successful. But now imagine scaling that to sending a robot into a hospital kitchen or into the home of an elderly person, and then solving these kind of tasks in such open-ended environments. Is still a question how far we can go with pure simulation. I can well imagine that we will have to augment that data also with real-world training then.
And Seungwon, how about the issue of data? You know, in language, there are scenarios where I imagine things like low resource languages where you don't have enough data, or maybe in dialogue systems where you don't really have full conversational data of lots of training examples. What do you do in that case?
So after hearing from robotics side, I think I'm viewing generative language AI as a sort of simulator or experimentation. So there is golden sort of annotator coming from human, but we can also obtain, like having a generative AI means we can have sort of silver annotation coming from, generated from models. So it can be potentially noisy, but there is also plus side of getting in any arbitrary angle that we need. We can collect, we can control how to collect observations. And if you sort of aggregate all those simulations, sometimes it can really complement human annotations. So I'm interested in this interplay of observation and sort of noisy experimentation together, building sort of the model for understanding, reaching to the understanding or the model.
But you know, there are techniques in language where if you have, say, a low resource language, you would take English and use a translator to try to generate, you know, generate essentially examples in this other language that you would then try to train directly on. But obviously there might be some concerns there of domain shift, or that, you know, you're relying on the translator to be accurate. Is there, well, how, you know, are those issues coming up in language?
Oh, yes, yes. The transfer that you mentioned, like translating, to transfer from high resource language like English, translator can work, and not surprisingly work well for languages that are linguistically similar. And then sometimes this transfer can be negative if the language is far from, in terms of language family or in many aspects. But if they're close enough, this translation is a good technique. And then, of course, noisy, but I guess the point I wanted to make is that you can collect many noisy observation and come up with a better, more robust generation for this transfer case.
Okay. And then another aspect I think that was interesting that's common is the idea of, both of you talked about kind of action generation as the output, right? So how is action generation different than sequence generation that we think about in natural language, right? Is there different constraints? Is there, what do we have to worry about when we actually have something that's actually interacting with a world and changing the world to a set of actions? What do we need to reason about there when we build the models or train the systems, as opposed to just generating a sequence of tokens at the output?
I can
go ahead. Please go
ahead.
No,
go ahead.
I think the main difference is I have to keep my state and the word state, because if I make some action that brings up changes in the word and my state, and in my talk example, I put the wire down. I no longer have wire, so I cannot put the wire down. So it should be crossed out from my generation list. But it wouldn't work like that if you are treating like ranking by plausibility. So this kind of tracking, I think, can solve language generation more coherent as well. So there are redundancy and conflict issue which can be handled by very sort of simplified word models of, did I say this fact, and so on. So having this additional goal helps for robustifying, I think even for generic language generation.
And I think in robotics we've seen, on the one hand, we just also had some recent work where we used GPT-3, for example, with prompting in order to translate human commands into actually Python code that then describes kind of the high-level control structure that the robot should follow to execute the command. So on the one hand side, I'm continuously surprised by how extremely capable these language models are nowadays already. Of course, the big problem is still that even from these descriptions, you still have to what we call ground these symbols, right, in actions in the real world and in visual perception in the real world. And when we talk about lower level, let's say, control commands with continuous spaces, then we've seen on the one hand side already successful applications of transformer style sequence modeling for tasks like what we call behavior cloning or imitation learning, which means you give the robot multiple examples of certain tasks, and then we treat this as a sequence prediction problem, and then the robot, the model generates actions. One of the problems that is certainly still relevant in that domain is what we call the domain shift that comes due to the sequential nature of the problem, which means if every action that the system generates, if it slightly deviates from the demonstrated data, for example, then over time, my robot, as it's executing these actions, might get further away from the training data because of the sequential nature of this. And the world kind of deviates from what the robot expects to see. And then suddenly my model is in a domain that it doesn't have any training data in, and the robot just might not know what it should do anymore, or it might just generate worse and worse actions. So there's been, of course, several techniques that have been applied in general in the machine learning and the learning community in robotics. And some of these can also be applied to these sequence models in order to make it more robust.
Mm-hmm. So I guess then the issue of the, when you do these kind of sequential actions, that kind of tracking the world state properly over time is very important. And we heard, one way of doing this is to think about a continuous world state where, everything is kind of, continuum, and you have parameters, and you're tracking real, locations and voxels or whatever it is. Another way is to do it more linguistically, right? To have some sort of semantic, linguistic representation of what the world is, that the red block is now on top of the green block, and that the drawer is open. Do we need more? Should we be using language? I mean, I think in your game, language was the world representation in some sense. Right. Do we need that more in robotics, or is that good enough, or is that how humans do it? What should the world representation be?
I think unfortunately, I'm not very good I haven't studied much about robotics, so I may be, I'm not an expert. Disclaimer first. And then I think you can gain from language, and also there is some critical disadvantage of using language. And what you can gain is, I think you can use plausibility as some kind of, you can transfer from human prior or language prior for planning purposes. And then I see some work claiming that using that information as an additional source is useful. But downside is that it is highly ambiguous. It is very difficult to define semantics for language alone. Regarding the previous question, dealing with sort of robotics or text-based games has advantage that we can clearly define semantics for language because it generates action, and that based on the outcome, we can compare like two states that are equivalent. We can sort of formally define semantics. It may not work for general language statements, which can be an obstacle for robotics. So in language side, we see lack of compositionality, lack of understanding structure. Shared structure is what's lacking, so we are working a lot on teaching the composition so that even when we know one template and another, we understand the semantics of the combination, which current language like NLP 3.0 is very poor at. So for that, we shouldn't treat language as a sequence, but rather templates and its composition, which requires more work. But at this current state, it has both, I think, opportunities and challenges for robotics.
But what is the state of the art in kind of these text-based games now, right? Does AI perform just as well as humans at reasoning about, world states that, you have to open the door to get to the room and then you have to move objects, that kind of higher level kind of reasoning and planning? Is AI just as good as human level performance now?
Oh, I don't have answer. I don't have number right now. I need to check, but
it's close.
It's close. I think it's good. Yeah.
Okay.
Yeah, I think these models are very good at this high level reasoning, right? But there's still the gap, of course, again, to this grounding in then the real perception and the real world. We see this that often there was some work, for example, the SAIF work by the Google team, where they also use large language models first to kind of generate sequence of actions. But then it turns out that most of the effort really went actually into somehow training the robot to execute those individual actions. So, and that turned out to be way harder than training the language model actually to generate them in the first place. And regarding representation, I think it's really a very active and it's very open question in robotics right now, right? Like how explicit 3D should a representation be? Could we just do it based on visual input information, just 2D RGB images? Or does there inherently have to be 3D in there? Also, the question you were talking about compositionality. We did some work on for robot manipulation for multiple objects, where the goal was rather than generating a single embedding vector, for example, for the whole scene, what we aimed at was we trained a network that would generate an embedding vector for every object in the scene. And these embedding vectors were trained such that they could answer questions like, oh, is the one block on top of the other block? Or is an object in the robot's gripper? So it was more trained to answer these semantic questions. And we hope that by having such a representation, it lends itself then also better to compositionality structure that we would like to have in these reasoning systems. So, but in general, there's various kind of different efforts going on. And I think we're just at the beginning of really looking at this.
So yeah, I guess the question then is, building in compositionality or being able to do these intermediate readouts, Is that important? Because there was also a trend of saying everything should be just learned end to end. Just put it all together and just train it, and it'll naturally, things will naturally, get put in place and learn. So is it important to kind of put those in as constraints, compositionality or modularity or any of these kind of internal representations being able to do other tasks? Either of you?
So in my experience, I would say, so for example, we're looking at various aspects of that problem. So in some work, we're trying to see what happens if you impose these constraints. And in that context, we have seen that these other models that don't impose any of these constraints, that just, for example, again, generate a single vector for the whole scene, that if you query these models then, so for example, if you want to be able to reason about individual objects and their spatial relationships, that those models don't work very well. So in our experience, actually, during training, trying to leverage or impose some of these constraints can be beneficial, which doesn't mean that I don't expect that these other techniques with sufficient data might be able to learn similar structure without the explicit constraints in them.
Mm-hmm. And Seungwon, you argued that you need this for robustness or other.
Yeah, I think my experiences coincide with that. Having constraints sounds negative, but it usually was positive for robustness, because I think maybe action space is too large for genetic language generation or like vector representation. So at this point, from my point of view, I think having constraint is a good idea.
Mm-hmm. So causality or other types of other sources of information that you have to match to in some sense.
Yeah.
Okay, I see. Yeah, I guess in terms of then for the future, what do you expect will be happening in the next few years? Like, will we really be able to have robots that clean up our kitchen for us, Dieter, or will we really have these agents that we can answer our questions for, or moderate a discussion panel at some point with an AI agent? Maybe can we have that in the near future? What do you expect?
I hope we'll see some progress on the manipulation side, especially in these environments, hopefully also through a mixture of large-scale training and simulation and then fine-tuning with real-world data. For that, we also have to come up with stronger algorithms such that the robot can perform this lifelong learning and training in these environments and in the real world. At the same time, we know these things always take much longer than we think or hope they do. Like look at autonomous driving, right? You remember when it started, we all thought that by now nobody needs a driver's license anymore, but we're still not there yet, right? But I think I really do hope that we will see some strong improvements over the next few years.
Mm-hmm.
Yeah, maybe no robot panelist next year, but I think maybe there will be lots of AI augmented tools to help this conference better. So for example, maybe I think the translation is one great live demo, and maybe they can show related information, or they can create information for different expertise level. I think many like NLP tasks discussed in the paper levels can be applied for real communication in the next years of Samsung event.
I see. So more domain-specific types of approaches that may be personalized to individual users. Okay. And yeah, we have a couple minutes. Any last words or advice to some of the students out there or people who are interested in these areas? What do you see as exciting areas that they should try to pursue or study? Dieter?
Well, I would just say it's super exciting times right now, right? I see the power of deep learning, especially, for example, also just in the ability to kind of bring different research strands together, to bring control and perception, to combine them. And also, it's almost like a language that now many different communities speak, and it enables suddenly collaborations that weren't possible beforehand. For example, language and robotics. So I'm sure that there's many new exciting fields coming up, and students should just go for it and have fun.
Yep, same here. Exciting topics, exciting time, and we are looking for lots of creative ideas to overcome lots of issues discussed in the talk and in the event.
Yeah. No, I agree. I think if you look at kind of, as Dieter mentioned, in the past, people trying to do language and robotics were very few number of researchers, and they were very limited in techniques. They were mainly very constrained, scripted types of models that were used on the language side, or there were very simple behaviors that were used on the robot side. We hope that with the scaling of these types of algorithms in both domains, that we will be able to get things eventually that where we're talking to robot assistants in natural language, and they're able to fully comprehend and respond in natural ways to it. So we hope, and we hope that we'll see these developments soon. We hope folks from industry as well as academia will be able to contribute to these. So please join me again in thanking Dieter and Seungwon for their thoughts tonight, and we hope that we'll can be able to continue these fruitful discussions in the future. So thank you very much.
Yeah. Thank you.
Great. All right, that concludes.
If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. If you have any questions or comments about sessions or speakers, please leave them on the Q&A board at the Samsung AI Forum website. Next is Lightning Talk by Taegeon of Samsung Research. Hello, Taegeon.
Okay. Hello, everyone. Thanks for attending my talk. I'm Taegeon from Samsung Research, data research team. Today, I'm going to talk about accelerating deep learning training pipeline, which is our ongoing work. Let's get started. Nowadays, there are various deep learning models with diverse purpose, such as ResNet for image classification and GPT-3 for natural language processing. Then, how to train such deep learning model? Let me briefly explain the end-to-end deep learning training pipeline. First, we need data sets for training, so various types of data are gathered as raw data, and the raw data are converted into the training data with data cleansing and formatting. And after that, model developers design and implement their model architecture using existing deep learning framework, such as TensorFlow or PyTorch. And these systems execute the training job on the GPU cluster and cloud resources. And for training, the training data are then loaded and pre-processed on the CPU with decoding and augmentation, and the pre-processed data are then fed into the GPU for gradient computation to update model parameters. And usually, transforming raw data into the training data, which we call offline pre-processing, does not frequently happen during training. On the other hand, the data loading, pre-processing, and training on GPU frequently happen hundreds of times to update the model parameter. So maybe this may take several hours or days according to the model size. So model developers must wait for a long time to finish their training job. Then let's imagine that if the training just takes a few seconds instead of a few hours, then maybe model developers can explore better model architecture and parameter quickly, and therefore, reducing the training time and accelerating the deep learning training pipeline is really important for developing better model. Then, how to reduce the training time? A simple solution is just use more money. So we can reduce the training time by using more high-end, expensive GPUs, and also we can reduce the training time by adding more GPUs. But does this always guarantee the training speed up? So to answer these questions, let's deep dive into the deep learning model training in existing frameworks. Usually, existing frameworks execute the training for each mini batch, and to minimize the GPU idle time while training, they support some pipelining or prefetching. So while the first mini batch are executed on the GPU for gradient computation, the second mini batch can be executed on CPU for preprocessing, and so on and so on. However, the GPU can still be idle if the time to process data on CPU is still longer than the time to process data on GPU. And therefore, even if we reduce the training time by adding more GPUs and by using more expensive GPUs, if the CPU becomes the bottleneck, then the training speed will not be improved. Recently, we have observed that various deep learning jobs suffer from such CPU bottlenecks because of diverse reasons. For example, because of high decoding overhead of large size of data, and due to the complex augmentation that requires CPU-intensive operation, existing training jobs suffer from the CPU bottlenecks. So to address this problem, our team developed a new technique that automatically offloads preprocessing to remote CPU resources. Our idea is simple. When there is no CPU bottleneck in training, then we do not offload. Otherwise, we try to offload some of preprocessing operations to remote resources to minimize the CPU bottleneck and accelerate the deep learning training pipeline. However, there are several challenges in realizing this idea because we must automatically decide when to offload and which operations to offload and how much data offload to the remote resources. Naive decisions may lead to performance degradation. For example, if the remote resource has low CPU capacity and low network bandwidth, then naively offloading all preprocessing operations to the remote resources may lead to the remote resource bottleneck and the performance degradation. So to address the challenge, we design and implement FastFlow, which is a system that automatically decides offloading decisions on top of TensorFlow. Here, let me briefly explain how FastFlow executes a training job and automates such offloading decisions. First, users write their training code using FastFlow's API, but users only have to provide some additional configurations for offloading without modifying the main training logic, because we extend the existing Keras API, which is a popular API for model development. And FastFlow, to execute the user code, FastFlow transformed a training job into a directed acyclic graph, which we call DAG. And FastFlow profiles some performance metrics of the training job before the actual execution to make offloading decisions based on the profiled metric. And FastFlow also minimized the profiling overhead by executing a few iterations of the mini batches instead of fully executing the whole training job. And based on the profiled metrics, FastFlow makes offloading decisions. For example, to decide when to offload, FastFlow compares the preprocessing speed on CPU and the gradient computation speed on GPU. So if the preprocessing speed is more slower than the gradient computation speed on GPU, then FastFlow detects CPU bottleneck and tries to offload some preprocessing operations. And to decide which operations to offload, FastFlow compares several candidates for data pipeline by modifying the original input pipeline and offloading some preprocessing operations to the remote resources, and choose the best data pipeline that leads to the maximum training throughput. And to decide how much data to offload, FastFlow considers computing capacity and network bandwidth of remote resources. For example, if the remote CPU throughput is 2 times larger than the local CPU throughput, then FastFlow tries to process 2 times more data on the remote resources. We have evaluated FastFlow with various workloads on diverse resources, and also we compare FastFlow with diverse systems. Here, I will show some of the results. Compared to TensorFlow without offloading, FastFlow improves the training speed and also increases the GPU utilization. But in fact, it seems obvious because FastFlow uses more resources for offloading compared to the TensorFlow without offloading. However, the key point is that FastFlow automates offloading decisions without user intervention and achieve the optimal performance. And we also evaluate TensorFlow with manual offloading, and we also confirm that FastFlow is still better than the TensorFlow with manual offloading because of the optimal decisions based on the profiled metrics. Okay, in addition to the FastFlow, I'd like to introduce some our ongoing and future topics. Our team is interested in scaling and accelerating end-to-end deep learning pipeline. So, for example, we are interested in scaling deep learning jobs on heterogeneous GPU clusters. And also, we plan to develop some lightweight GPU sharing techniques across multiple jobs to improve the GPU utilization. And also, we are interested in optimizing inference jobs to minimize the inference latency. So please feel free to contact us if you're interested in this topic and want to build the state-of-the-art techniques together. Okay, this is the end of the slide, but before finishing the talk, I'd like to announce that our FastFlow will be publicly available soon, so please stay tuned and give us time. Okay, thank you very much. You're listening.
Next is the last lightning talk by Naejin Kung of Samsung Research. Finally, it's your stage, Naejin.
Good afternoon, everyone. My name is Naejin Kung, and thank you for having me to present our work on whole robust wireframe detection. This work was collaborated and co-authored with Kyung Park and Harshit Kokar. Then let me start my talk with a typical endorsing example. Wireframe is a line segment-based representation designed to well capture the salient, in other words, prominent structure of visual scenes surrounding us. However, we often face that the underlying scene is occluded by a foreground object that is too large to ignore easily. Unlike wireframes, conventional edges and line segments are too spurious, therefore hardly aligned with the salient structure of the underlying scene. Wireframes, the existing wireframe detection methods may not be able to handle the large hole occlusion either. Our approach, however, is capable of predict the wireframes far more robustly across the large hole occlusion, as you can see in this picture. So before I talk about how we solve the problem, let me briefly describe the existing wireframe detection methods. Most of the wireframe detection models, how they operate. So the framework is composed of a backbone network as well as a matching and verification module. The backbone network predicts the junction and line maps, which are then converted to coordinates or already embed the coordinate information so that the junctions and lines can be matched to each other to have proposals. Then each line segment proposal is verified to assign a score. And finally, the line segments with high scores define the final wireframes as visualized on the right. However, this framework is not yet designed to handle large hole occlusion. So in order to handle such a problem, we propose three novel ideas on top of the basic framework, which are the conditional training, RGB GAN, and pseudo-labeling. So let me explain each of the modules one by one. First, our conditional data generation method and training technique let the model understand the holes. We train the model with images with hole by superimposing real-world foreground object silhouettes along with the corresponding binary mask maps with the hole and the ground truth wireframe annotations. For more effective conditional training, we progressively increase the hole size along with a larger number of epochs during training. And we also found that by placing the hole while avoiding the isolated components further improves the effectiveness of conditioner training. Second, we introduced so-called an RGB GAN, an RGB generative adversarial network, which lets our model better understand the underlying hidden structure of the scene beyond the holes. As you can see in these examples, during training, our RGB GAN regenerates the hidden contents of the scene beyond the hole effectively. And this capability is maintained in the backbone network. Therefore, at inference time, we can safely remove the RGB decoder part, and still our model knows to predict the underlying structure better. Finally, we introduce semi-supervised learning with pseudo-labeling, which enlarges the model capacity even further. For this end, we first collect large-scale pseudo-labels by applying an ordinary wireframe detection model trained on a smaller scale, manually labeled ground truth wireframe dataset without hole. We then filter out inaccurate or too sparse cases in a statistical manner from the initial pseudo-labels, which gives the final pseudo-labels as visualized above. We then superimpose the whole mask by applying our conditional data generation method. And finally, we perform semi-supervised learning on this pseudo-labeled data, which then again fine-tuned on the ground truth small-scale wireframe dataset, which is again extended with holes by applying our conditional data generation method. By applying those three approaches all together, let me show you the results from now on. The existing models shown on the left may leave an empty area where the hole rotates, or mistakenly detect false line segments around the hole boundaries. On the other hand, our approach understands the hole occlusion and underlying scene composition better, therefore robustly detects wireframes across the large hole occlusion. We can continuously confirm this by checking out more examples, just like this example, which is challenging due to lots of vertical lines, and a kitchenette example, and a living room example here. Also, ours still works robustly on the outdoor scenes as well, as you can see in these examples as well. Also, we found that our approach still works well and even improves the ordinary wireframe detection without hole as well. Let me show you a couple more examples. And I'm going to show numbers to clarify this even more clearly later. Here, let me show you real-world examples with significant foreground objects. Existing models fail to detect wireframes across the foreground regions, while ours, combined with an automatic segmentation method to provide a mask, robustly works on such significant foreground occlusion. In this example, please focus on the vase area on the right bottom corner. And also, in this challenging example, due to the extremely dark background, there is a crouching person on the corner, and ours still works fine, regardless of this challenge. So we evaluated our model compared to the recent existing models on the standard wireframe test set with and without hole. As you can see in the table, in the last row, ours works the best compared to the previous works compared with And we can show this even more clearly with the precision and recall curves here. So the red curve corresponds to our full model, and compared to the existing works, ours works significantly better than them, as you can see in this picture. At the whole size, 10 to 30% of the input image size. At the whole size, less than 10% of the input image size, and even without whole. Also, here we show the effect of each module in our full approach. The green curve here corresponds to our approach that applies the conditional training and RGB GAN, which already outperforms the baseline model shown in the black curve, and the red curve corresponds to our full model, which even further improves the performance. We can continuously confirm this at the whole size, less than 10% of the input image size, and even without whole as well. So in conclusion, we proposed a novel approach to detect wireframes in a whole robust manner, and our approach is robust to whole occlusion and even improves ordinary detection without whole as well. And I'd like to tell you another point that our approach is highly flexible. Therefore, it can be applied to most of the recent models that share the similar basic framework. So this concludes my talk, and thank you so much for your attention.
Last but not least, Daniel Lee, Corporate Executive Vice President of Samsung Research, will deliver the closing remarks. Please welcome Daniel Lee.
Thanks for coming. I think we all enjoyed a wonderful day of talks and discussion. I want to encourage you, if you're interested in these areas, to follow up with us, find out more about some of the projects you heard about, some more details. So, again, we're so excited to host you today for our AI forum. I think for those of you who are actually here in Umyeon, stick around, because I think we have a lucky draw. So some of you have a chance to win some prizes if you are here till the final end. But for those of you online and everywhere else, thank you so much for joining us. Thank you.